Hello everyone, welcome to the RAS G meeting on system scale observations and modelling of solar wind magnetosphere, ionosphere, thermosphere coupling. Sorry, we're slightly late getting started. This session starts now and will last until 11:40, at which point we'll break for coffee and other such lovely things. And we've got Colin Waters, Daniel Billett and Jenny Carter in this first session. And our first speaker is the keynote speaker, who is Colin Waters. Colin is a speaker at the University of Newcastle, a researcher at the University of Newcastle in Australia. And he has done too many things to adequately summarize in my introduction to his work. But kind of highlights are that he is a large part of the driving force behind the Ampere dataset, which some of you will be aware that I work a lot with. And is a fantastic resource for the community. And he has also recently co-edited an ISI book, which deals with how to do kind of large data set stuff from multi-spacecraft measurements. And Colin's going to be talking today on southern and northern hemisphere field line currents and magnetic fields from Ampere. So thank you very much for coming, Colin. And if you hit share screen,
right, the first thing, sorry.
Oh, yeah, I can see your screen, brilliant. And then, yes, excellent, I can see the slide. Two very quick things before you get started. Firstly, this meeting is being recorded and will be available through the RAS at a later date. So everyone just be mindful of that. And secondly, if anyone needs live transcription, there should be a button on your bottom bar that says live transcript. And if you click it, that will, that should start live transcription for you. If it doesn't, please put it in the chat so I can ask the RAS to get that sorted. Thank you very much. Colin, I'll let you take over. Thank you.
Thanks, John. And thanks for the invitation. I see that there are a number of presentations today that deal with the Ampere data. And John asked me to talk about that particular data set. As he mentioned before, it's been used quite extensively since it came into being in 2001. So I thought in this talk, I would go through and give you an update on some of the latest things that we've done with the Ampere data set, and in particular in having a look at improving the data that we get from the southern hemisphere and why we needed that improvement. So as you may be aware, the Ampere data set is derived from the Iridium satellite constellation, and in particular, the data comes from the Fluxgate magnetometers, one on each spacecraft, as you can see here. So in summary, the constellation is 6 orbit planes in the red there, and 11 equally spaced spacecraft in each orbit plane, denoted by the green dots. And the magnetometer is part of the attitude control system, the avionics on each satellite. Of course, the Iridium constellation is about selling data and communications. Brian Anderson saw that it was an opportunity to use the magnetometer data from the attitude control system for space science. And this happened in the late 1990s when the Iridium satellite constellation was being launched in 97, 98. I first heard about the project at, I think it was an IUGG or an IAGA meeting in Birmingham in the UK, where Brian and I chat about it, and then I did a sabbatical at Johns Hopkins University in the year 2000, and we got going with some of the data and the data fits. So the constellation has the 6 orbit planes. There's about a 9-minute spacing given the altitude orbit of 780 kilometers, and the spacing of each spacecraft on each plane gives you about a 9-minute delay before one green dot can travel to where the other green dot was at that time, to give you a full coverage. So the polar orbiting, they cover the whole of the Earth, and in particular the auroral zone is what we're after. So here is an example of some of the raw data as it comes from Iridium. And this data is some of the first data, as you can see here, from 1999. And the top panel shows you the data from the magnetometer straight from the Iridium avionics system. Each of these loops you can see is one orbit pass, and this is a data section over a 24-hour period. You can see here some missing data and some other offsets. So that's the data input. And the next thing that has to happen is that we want to be able to take off the perturbation of the magnetic field. So you've got fields of up to 10,000 nanotesla, and you're looking for the perturbation fields of the order of 1 or 200 nanotesla. So there's a magnetic field model subtraction that goes on, and then the matrix correction is really a complicated process of trying to sort out what the attitude control system is doing on the spacecraft so that you can actually get, to the best of your knowledge, the components of the magnetic field perturbations, which obviously depends on the orientation of the magnetometer in space. And then finally, there's some filtering done, which hopefully will get the perturbation magnetic fields off. And this is called the pre-processing section, and Brian Anderson is in charge of that process. So over the years, beginning in '97 through to the present, there are actually 3 types of Iridium data. So the first set goes from about 1999 through to 2008 or 2009. And these data have the attitude information coming from the combination of the gyro, the magnetometer, horizon and the sun sensors on each of the spacecraft, with an uncertainty around about 0.2 degrees. And this is important for particularly calculating the radial component of the magnetic field, which has always been of poor quality for the Iridium data because of the attitude control uncertainty there. So the data from 99 through to 2008 or 2009, start of 2009, were sampled at 200-second intervals, which give you a coarse sampling, particularly with small-scale field-aligned currents. In addition to that, it was cross-track data only because of difficulties with the attitude control information. And so there was just the one component, a cross-track of the spacecraft trajectory. From 2009 onwards, there's the second type of data, and the attitude control information and the processing were improved. The data sampling went up to 19.4 or 20-second data, and then there's a burst mode of 2-second data, or 2.16 seconds. And we had the ability to have burst mode if we knew that there was some interesting event coming, which of course the price for that data went up as well. So it was used sparingly, but there are some intervals of 2-second data. Iridium recently replaced all their hardware. Starting in 2017 through to 2019, they've replaced all of their satellites to what they call Iridium Next. And the attitude information is much better at 0.02 degrees via the star camera. The magnetometer is still in the attitude control system. And it still has the same digitization floor of 30 nanotesla, a different model of magnetometer. And this is at a fixed 8-second sample rate. And we do have some of those data, but they have not been released. We're still doing testing on those. So keeping that in mind, there's the Block 1, 97 to 2008, Block 1, 219 to 29 to 219, and then the next 3 sets of data in the top panel here. And the description of what's going on with the Iridium Next data was given by Brian at the AGU meeting a couple of months ago. Yeah. The pre-processing is what I described, taking the data that we get from Iridium and removing the main field, correcting for the attitude control and other processes. And this is called the pre-processing. And here are the references for the way that that's described. For the way that it's described with the Iridium Next, all we have is, at the moment, because it's new, is Brian's AGU poster. After the pre-processing, then there's the basis function fit to develop the Ampere data products, the fitted delta Bs and the field-aligned current. And so from the data set from 97 through to 2009, then there's this GRL, which describes that process. And it particularly talks about just the cross-track component, just the one component, as well as David Green. So the data from 2009 through to 2019, and also the Iridium Next, this data, science data products for Ampere in the ISI book is the appropriate reference for the Ampere data products, the fitted data. Right, so I'll talk more about these acronyms in the next couple of slides. Here is an example of the first set, the cross-track only data we have from, I have data from 99. I don't think we have data pre that. If we do, it's for testing and it has a lot of noise in it. But certainly from 1999 onwards with the cross-track only, we have those data. They're not available on the Ampere website because they are cross-track only, and you need a half an hour to at least an hour to collect the data because of the sampling, 200-second sampling. And so really they're only relevant for intervals where you have a fairly constant IMF or constant conditions. But here is an example of the red in this panel is the input data collected over an hour. Then you have the fitted data on the right, and then the tracks and the east-west delta B in a color magnitude, and then on the bottom right is the field line current for that particular interval. So from the 20-second data then onwards, from 2019 to the present, here is an example on the left of the data that is currently available that people have been using. 20-second, it can go up to 2-second burst mode. And on the right is an example of the additional spatial resolution that we get if we sample that at 8 seconds. It's not the same interval. This interval in 213 is actually burst mode 2-second data, and we've downsampled it to 8 seconds to give you an idea as to the density of data that you would have with the next that's coming. Right, so the actual processing after the pre-processing. So we have the input delta B that comes from Brian's pre-processing in NetCDF files. You select a 10-minute segment and convert to geographic. Then you calculate the Iridium track intersection point, and you calculate a rotation matrix based upon that so that the fit is centered on the track intersection. Shift that data into that coordinate system, do a spherical harmonic analysis on that, calculate RMS areas, generate the uniform grid, and output the IRD and GRD data. So the IRD data that you have is the Iridium data. That is the data that has been pre-processed and just gives you the delta B after Brian's pre-processing. The GRD data is the data that you get after the spherical harmonic fit and includes the field line current. Right, so all last year I worked on refining this code for a number of reasons, which I'll explain in the next few slides. But essentially the red pieces here are the new bits. So instead of having a spherical harmonic cap fit center based upon the Iridium track intersection, we've now moved it so that it is centered on the actual data system. So the maximum delta Bs, and I'll give you an example in the next slide. We do the fitting in GEI rather than shift to GEO. And then we do a spherical elementary current fit first, and the reasons for that I'll explain in a moment. And we insert that before we do the spherical cap harmonic, and then the rest of the process is the same. So the two main changes for the new processing, which I've only just finished the code last month, are the change in the fit center and a extra fit from the spherical elementary current systems. Okay, so why are we doing this? Well, the difficulty with this, particularly with the Southern Hemisphere, has been the offset between the Iridium track intersection point, which would be around about here, and the center, if you like, of the actual system, which I put a little C here and circled in red so you can highlight it. And you can see that this offset is significant, and certainly in the Southern Hemisphere, This is for a northern hemisphere case, and it's not too bad. But in the southern hemisphere, it can be up to 15 or 20 degrees out. And so if you're doing a spherical harmonic fit in longitude around this particular center, then there are going to be some cases where the distance in longitude between data is larger than others. And so setting a particular expansion order in longitude for the spherical harmonic caps becomes problematic. All right, so that's the basic reason why we wanted to move it to a data centered. The other reason is that if you're going across a harmonic in longitude around the blue circle, you're cutting across currents, and they can cause problems with a finite sum in the spherical harmonics. I'll show you an example in a moment. Right, the next step in the new processing is to add in the spherical elementary current systems. So you can see little S's, I hope, on this slide, identified by the red. These are where we put the sec poles, and the little B's where we've located where we will get the delta B fit from the spherical elementary current system. So we've shifted, as you can see, the system based upon the maximum delta B's rather than the Iridium track intersection point, which is up here. And now if we're doing a spherical harmonic fit in with a longitudinal order, you can see it's going to fit this particular circle much better than cutting across them. The location of the little B's where we're going to calculate these fits is according to the longitudinal order you choose, and also if there's any missing data in the tracks, we insert a point in there. So basically what happens is that the input data shown in the blue and the fitted spherical elementary current system data shown in the black now all goes into the spherical harmonic fit. So here's an example of the SEC fit, the theta component along the top and the phi component along the bottom. And these are just ordered by track. So this would be track 0, track 1, 2, 3, 4, 5, as you can see. Here are the auroral currents in each track. And then the last ones are the ones that we've added in this group here. So you can see the fit is quite good with an RMS fit. There are some little details in here that if you reduce the algorithm in such a way that the, what shall we say, it's a singular value decomposition process where you're adding in eigenvectors, and the more you add, the better the fit, but the worse the data looks where the data isn't. I can explain it like that. So there's a little bit of juggling going on there and a few tests that we've run to make sure that we have it the best we can. So here's the final product. The blue are what you'll get in the GRD files on a uniform AA CGM grid. And on the right-hand side is the field line current from that fit. All right, so a comparison then. So for that particular interval for the Northern Hemisphere, the top panel here is the present data that you can get from the Ampere website. And the bottom panel is the new processing that I've just described. And as you can see by looking at the field line currents, they're fairly similar. And what I've found so far with the testing is that for the Northern Hemisphere, there's a few small changes, but they're mostly the same. And so that the data you have been using, if it is for the Northern Hemisphere, then there are only some small changes that will come with the new processing and should be fine. However, for the Southern Hemisphere, you can see that there's quite a difference. So the present data from the Ampere website gives you this result for the field line current on the top here. But the new processing, as we have hoped, has given us some more continuity where we think there should be based upon the data, because you get used to looking at the input data, where the delta B's are and where the current should be. And certainly around here where the delta B's are large, you would expect some field line current to be, and that's what we're getting with the new processing as opposed to some gaps for the older processing. And you'll notice that the offset from the track center here and the actual delta B's is quite large for the south, which is what is causing this particular trouble. All right, here's another one that I've selected, and it shows quite it's up to 16 or 17 degrees offset, where the Iridium tracks intersection with the present data processing. The center of the spherical harmonic fit would be in here, whereas with the new one, it's more in the center of these delta Bs. And so once again, the present data products in the top here and the new ones down on the bottom for both the delta B. So the center panel would be in your GRD files along with the field line currents on the right. And the input delta Bs here on the left, these are what you have in the IRD files that you can download, and they haven't changed. So looking at a storm interval, and I've chosen the St. Patrick Day storm in 215. In the top panel here, we have the IMF, and it's the black curve here, which is the BZ component, and BY in the blue, and so on. The total is in the green. So what I've done here is just averaged the field line currents in all MLTs and plotted it as a function of latitude, ACGM latitude, with the average current in the color. So you can see the storm began here. The currents don't actually light up right at the very beginning. They actually build. There's an expansion in both the northern and the southern hemisphere. And then you'll notice as the BZ component goes northward, then the currents actually expand back poleward and diminish. And then as the BZ comes further south, the currents intensify, and as well, if you actually trace along there and up there and back down there, it actually traces pretty well with the black line of BZ. It's quite remarkable. And as the BZ component in the storm subsides, the currents contract poleward again and diminish. So this is the current north and south data. What happens when we pass that through the new processing? So for the northern hemisphere, they're basically the same. And here are the southern hemisphere comparisons. So the top panel shows what you would get from the MP website, and on the bottom panel is the new processing. There are two things. First is that the currents are a little bit stronger for the new processing, and there are also some features in here which are appearing that perhaps weren't appearing in the old one. So this particular structure is a bit stronger here compared to here, and there are some other small things here. But overall, we're getting a similar result. There are just some particular differences, and this is for all MLTs. And so to try and unravel perhaps where we're making a difference, I've chopped it up into MLT sectors, which is this particular plot here. Now, I originally plotted it in 2-hour intervals so that we had 12 plots all down the page, but that got a little bit busy. So I've decided on 4 6-hour blocks here, basically day side, over noon, afternoon, and then around midnight. So what we have here is the northern hemisphere for that particular storm, from 04 on the 17th through to 04 on the 18th of March. And the black lines are the new processing, and the dotted lines are the present processing. And as you can see, particularly through this particular section through here, the previous processing, the dotted lines, is a little bit less. So we're getting a little bit more current with the new processing, except for this particular MLT. You can see here where they switch over, and the old processing actually is a little bit larger. So there are some MLTs which are greater with the new processing and some a little bit less. And we're still trying to understand where those particular differences are coming from, and certainly whether we've got it better or, well, yeah, we've got it better, what tests we can have to see if we actually have it better. Certainly from these particular plots back here, when you're looking at the delta Bs, it appears that we have the currents much more accurately in the southern hemisphere, but then there are some other tests that we need to do to make sure. So that's the northern hemisphere. These arrows here, the 10 and the 13, correspond to these cessation and continuation of the currents according to the BZ in those times. So you can see the differences in the MLTs there for those particular intervals that switch on and switch off. Noticeably here as well in the south is quite a sharp switch off here in this particular MLT sector, not so much in these others. Once again for the south, the present processing is less here, but not so much here. It's greater here. It's quite a large difference in this particular section and here. But on the whole, on average, we're getting a little bit more current with the new processing. All right, I just want to mention briefly, there are other things that you can do with the Ampere data, and here's an example from Kyle Murphy's paper in 2012, where you can just take the delta B, the IRD files, and plot them in this format, where you have a particular latitude range, and you plot the various passes as a function of time. So for a given track, this will give you a constant MLT, and it's like having a set of magnetometers that are fixed in a particular longitude that give you a range of latitudes. And certainly the 2-second burst mode data looks pretty good in this particular format. And if you've got a study where you've got some auroral arc or some auroral feature that you're looking at, and an Iridium track happens to go through that, then this particular format that Kyle has in his GRL is well suited to that particular study and does not involve any of the fitting, it just uses the pre-processing data. So that's a bit of a plug perhaps for the IRD data files. Okay, so in summary, there are the 3 Iridium data types that we mentioned. The next data, Brian and I had a meeting last week, and we're working on trying to make that publicly available. We just have to do a few more things to make sure we have everything squared away. For the IRD data files that you have off the Ampere website, they're the pre-processed delta Bs. For the fitted data, then we have this particular reference. There's a revised data fit process for the next data. We're also thinking about pre-processing the data that's already on the Ampere website, whether that will be done for all of it, since the Northern Hemisphere data doesn't change all that much. We need to do some more tests, but certainly number 6 is very important for this, any sort of data set, particularly with Ampere. You set a particular set of analysis parameters, and you do just let the computer go on those particular parameters, but there may be intervals in which some particular fitting parameters may be better suited to that interval. And so strongly advise that you contact the Ampere team when you're working with the Ampere data. So small differences in north, improvements to the south. Now we're up to our comprehensive testing and comparisons. These are in process to make sure that we have the best quality that we can for the community. So thank you. I didn't hear any bells, so I didn't see any flashing lights. So, and John is muted, so I guess I can keep going. Maybe I'll stop there.
Thank you very much, Colin. That was excellent. And yes, no flashing lights, because we've got plenty of time for questions, so that's great. If anyone has any questions, please drop them in the Q&A, and I can read them out and Colin can discuss them. I did just want to say, Malcolm messaged me during that talk to note that the ISI book I referenced at the beginning of the talk is open access on the CAA site. So if you would like to go and look that up, it is available to you. And we've got our first question from Sandra Chapman, who asks, is the IRD data cross-calibrated between all the satellites?
Cross-calibrated, Sandra. I'm not quite sure.
I
can mean I can
talk.
Right.
So what I'm interested in, I just wasn't clear, because you'll see in my talk later, what I'm interested in is actually using networks to compare observations. And we've been doing it with SuperMag, and we work with the data before it's been assimilated or mapped. So it's on an irregular grid. So this works even if the satellites are moving around, but of course you need everything to be cross-calibrated, you know, that so I can kind of look at all across all the tracks. And I was just wondering, okay, you cleaned up each one, but are they all kind of on a regular, you know, calibration before you then go and do, you know, the spherical harmonic stuff?
Yeah, so each track that I've described there, Sandra, is made up of multiple satellites, because there are 11 or 12 satellites in each orbit plane. So the data for a whole track is made up of data from 11 satellites. And all of those data are treated the same, if that makes sense. So all the tracks and all the satellites, the data from all of them are all subject to the same pre-processing process. Now, having said that, what we have noticed is every now and then there'll be a DC shift in one of the satellite data coming through, and you can see that in the IRD data. It comes up like a comb shape, where you'll get fairly regular delta Bs for a short portion of the track, and then it'll go away. And this will be because one particular satellite in the track has got an offset that got through the pre-processing, Brian's pre-processing. But certainly if you're interested in the IRD data, which of course is on an irregular grid, and for a particular interval, then your best source of information about those data is Brian Anderson.
Okay, thank you.
You're welcome.
Thank you very much. Does anyone else have any questions? I've got one, but I don't want to push in before other people. Although I will, because we don't have any left. So you've got these improvements in the Southern Hemisphere, which are great, and they look like they do an awful lot to address like some of the morphological issues that we see there. So there's been kind of, I published a paper in 2016 which showed that the two hemispheres had a kind of asymmetry in how much current was flowing in either. Does this effect kind of wipe that asymmetry out completely, or is it more of a morphological improvement than an addressing of the imbalance between the amount of current flowing in either hemisphere, would you say?
Excellent question. And one that we'd like to know the answer to in detail, John. The preliminary, because the code for processing the data, as I mentioned, I've only just finished a few weeks ago. So we're in the process of putting both the next data and also the data, the IRD data available already through the processing, and I've provided you some examples. So let me give you my initial gut feeling for the data, so to speak. And that is that for individual events, for the Southern Hemisphere, the pattern can be really quite different. If you're integrating in MLT for the integrated currents, then the difference will depend on which MLT you're sourcing it from. And the sort of differences that we're seeing in the integrated current is of the order of 5 to 10% for a total sum around all MLTs, but it can be much larger than that if you split it by MLT. So if you've done a study which compares Northern and Southern Hemisphere ampere data as it exists as an integrated current over all MLTs, then you should be pretty much on the money. But if there's a study that's focused on a particular MLT, then it's probably worth going back and having a look at it with the new data.
Okay,
I guess
cool.
that's my best shot at it at the moment, and we'll know more as we progress with the testing.
And do you know, I know that this is like a very difficult question, but do you have a feel for how long it's going to be until the updated processing results in files that the community can download? Do you have a feel for that, or is that kind of too difficult thing to estimate?
It's only difficult because there are lots of things I don't know. So, right.
That's fair.
Yeah, yeah, and one of those being, Brian and Sarah Vine's timetable on. See, one of the difficulties is that the design of the new Iridium spacecraft is a little bit different, and where they place the magnetometer and other instruments on the spacecraft is different to the previous hardware. And so when Iridium announced that they were going to give us some new hardware, new satellites, we thought, oh, good, we'll get into the design, we'll talk to them about putting the magnetometers in particular places. But then, of course, there's always this communication, what shall we say, disconnect between the engineers and the scientists when you're building spacecraft. And it turns out that once we started receiving the new NEXT data, there were a whole bunch of signals in there that weren't in the old set. And so it became a little bit more complicated to actually do the pre-processing. Now, in chatting with Brian last week, my sense is that they're close, but it's really up to Sarah and Brian's timetable to be able to provide me with the pre-processed data, the IRD data. And then once that's done, as I mentioned, the code to do the spherical harmonic fit is here. It's not at APL, it's here in my study on a computer. So I've developed it here. It's not available anywhere else. And so we also want to do some comprehensive testing as well. So we're looking at comparisons with other spacecraft, Delta B, DMSB, and some other things. And the other thing that, since you're talking about very difficult questions, let me add this one, is people, and I understand why, and people have been asking us about the uncertainty, the error propagation through the process. It's a valid question. We've had a few stabs at it, but it turns out to be rather complicated. And even more complicated now, I've added another fit level into the, into the process. So to be able to work out the uncertainty in the IRD data is fairly straightforward. And you can certainly ask Brian about what his estimates are for the uncertainties. But as far as the fitted data is concerned, we've provided some estimates in the uncertainties we think there are in the field line currents. They're at about 0.15 microamp per square meter level. But in this new processing, we have to come up with some methodology to try and work out a way to get some reasonable estimates for the uncertainties in both the fitted delta Bs and the field line currents. Now, whether, and this is related to your question, because whether Brian feels that we should do that before we release the data, or we do what we did before, we just got the data out there so people could use it, and then got badgered for uncertainty estimates, that's a decision Brian has to make. So there are a lot of things in the play. He certainly is hoping that he will have the next data, as you can read on the MP website. It's always, you know, it's coming soon. But we're hoping this year and hopefully within the next few months. But yeah, there are a few things to get done, and there are some things that may give us some delays depending on what we find as we progress. But certainly, if you are interested in the new processing for the Southern Hemisphere, or even for the Northern Hemisphere, then just email me. I can have a look at your event, see how it books, and then let you know whether, yes, you're okay to go ahead, or no, we're still working on that particular part of it. That's fine.
Okay.
It's not a problem.
Cool. Thank you very much. Right. Well, that was fascinating. If anyone has any questions through the rest of the day, please feel free to put them in the chat. And if Colin has gone to bed by then, we could always email him and kind of start discussions after the meeting, because obviously it's later in Australia than it is here. Thank you very much, Colin. That was amazing. Daniel, I'm going to ask you to unmute and I'm hoping that you can see the share screen button.
Yeah, I can.
So Daniel's going to be talking to us about large-scale thermospheric density enhancements. And I will post a message in the chat when you've got 2 minutes left, Daniel, so that you know what's up. Okay, thank you very much. Oh yes, we can see the slide.
Yeah, great. Yeah, so it's just gone 4 a.m. here in sunny Saskatchewan, so it's a bit earlier than I'm used to getting up. So I do apologize if I slur my words or anything like that, but I have drunk like a whole mug of coffee when I got up, so I should be okay. And my cat's come and listen too. So this project has basically been 7 years in the making, really, and it involves a pretty underutilized method for calculating pointing fluxes on a global scale using a combination of data from Superdawn and Ampere. Back when this project was first started, the overlap of the Superdawn and Ampere data sets was only a few years. The release data sets from like 2009 to when 2013 or 2014 when this project was first started. But now we have access to nearly about 8 years of overlapping data. So we finally have enough to do some statistics of pointing flux. And in this study, we're comparing it to CHAMP data. And in particular, we're interested in looking at the Cusp density enhancement. I have to give a big thank you to all my co-authors, really, because everyone apart from me were the people who like first designed this this project back when it was first started, and they were a big help in like getting the gang back together, so to speak, to basically finish it up and redo some analysis and like and submit it. So what is the Cusp density enhancement? Well, it's exactly what it sounds like. It's an enhancement of thermospheric neutral density in the Dayside Cusp region. And it was first observed by Luratal using CHAMP. And it was present during nearly every single crossing that CHAMP made of the Cusp. And that's this top panel up here, which basically shows a big peak of the air density as it goes over the Cusp region. They coincided with very large downward field line currents in this middle panel. But embedded within them at a very high time resolution were very fine scale and extremely large field line currents, which are like orders of magnitude bigger than when it's averaged over a longer time scale. This only happened in the Cusp region, like for instance, later on when it passed over the regular R1, R2 currents, there wasn't anything really going on in the fine scale data. So it was thought that these fine scale field line currents were contributing to the Cusp density enhancement. And that as a result leads to higher pointing fluxes, which is why I'm talking about pointing fluxes. So this whole thing might be a bit of a blast from the past for Colin Walters, because them and co-authors were the original creators of this method. So I'm really pleased to go straight after Colin. We use this equation to derive the pointing flux, which depends on the electric field and the perturbation magnetic field, which is the perturbation from the magnetic field from the main field of Earth. We get the electric field from Superdawn data, which is this on the left. It gives us a global pattern of the electric potential, where each dot here is where one of the Superdawn radars has measured some line of sight velocity. Then all of that data is combined together. We attach a global fit to that, and then fit for the electric potential, which then is directly related to the electric field. Ampere can give us the perturbation magnetic field in a similar way. When you combine all the data from the Iridium satellites and then do the fit, you get perturbation magnetic field everywhere as well. And then when you combine them together using this equation, you get something like this on the right, which is a picture of the global scale pointing flux. Now, obviously, we do have some error, depending on like some of the errors which Colin mentioned in the previous talk. but also we have some error, for instance, where there's not a lot of superdon data in certain regions. For instance, like here on the pre-midnight dusk side, there's not a lot of data constraining this fit, so we have to take that into consideration as well. But the crux of the matter is every single time step that we have for superdon data, which is 2 minutes, we grab the relevant ampere data for that, combine it together, and we can get a Poynting flux map. So we have Poynting flux maps extending from 2010 all the way to 2018, or to whenever the ampere data set cuts off currently. So the question we want to answer with these superdon ampere derived Poynting fluxes is if we can see significant Poynting flux in the cusp region on average, where that density enhancement was. There's a few things we have to remember though, mainly the spatial resolution of superdon and ampere before ampere next is released, at least, is quite coarse. It's on the order of hundreds of kilometers per bin size when you start averaging it up. So it might not pick up those very small scale Poynting fluxes. Also, if we average all the neutral densities from the CHAMP measured just over time, then the cusp density enhancement will probably just be drowned out by the regular background motions of the thermosphere, which is caused by solar EUV driven recombination. So we also have to deal with removing that background density. Removing the background density is pretty straightforward. This black line here in the top panel, or black triangles here in the top panel, is the raw CHAMP data, or how it's given to us at least, which is not entirely raw. We take a 5-minute running average, which is this red line, and then we subtract it from the black line, and we get this blue line. And that gives us a perturbation from the main field, where we're assuming that the 5-minute running average of the CHAMP data is basically the contribution of the background density, just the regular tides that would happen in the thermosphere. And then when we can take all the CHAMP data from the entire lifetime of CHAMP and average it up, bin it up into a similar bin as we do the superdon data, and we can get, and then we get average patterns like this one. And this really highlights the cusp density enhancement, basically, because we're only essentially binning the enhancements above the background level, which the density enhancement is. Yeah, so we chose 5 minutes for this running average, because if you go much longer than that, then suddenly the CHAMP satellite was in a completely different it could be in a completely different local time, completely different latitude, and thus basically looking at a very different region of the thermosphere, and the density will be quite different as well. So there's a balance that we strike by choosing 5 minutes, but we feel like this does a very good job of highlighting the cusp, and then we normalize that as a percentage above or below the background level. So this is what we call the perturbation neutral density. So I will address the elephant in the room before I keep going on, because some keen-eyed people may have noticed, hey, the CHAMP data set lasts from about 2000 to 2009, whilst the currently available and overlapping superdon ampere data set goes from 2010 to late 2017 until the ampere next data is released. So our justification for this is these go over quite a big chunk of the relevant solar cycles that they go over. So we are hopeful in the fact that these data sets are big enough that they form decent statistical averages of the Poynting flux and the perturbation neutral density. And so we're saying basically, it's fine. There's enough data and it covers enough different solar fluxes. And the good thing about our CHAMP data processing as well is it inherently removes the effect of changing solar flux at f10.7 because you're only looking at the perturbation. So we take all the CHAMP data, we do that processing that I mentioned, and we bin it by IMF. And this is the result we get, basically. We can see that for every single IMF orientation, BZ positive, BZ southward, BY positive, BY negative, the cusp density enhancement is like very clearly apparent for all of them, which is what we expected, because it's been shown before that the cusp density enhancement is ever present, or nearly ever present at least. A few things we note by doing it this way is we see a BY asymmetry for the cusp density enhancement. For instance, for BY positive, it's a bit more towards the dawn side, and for BY negative, it's more centered around noon. Also, another interesting thing to note is percentage-wise, above the background level, the perturbation neutral density is fairly consistent across all IMFs, which is interesting. You might expect it to be more for under southward IMF, but it's not particularly that much more. That's interesting. And here's the results of taking all the ampere and all the supernon data and combining it together and doing the same averages and binning by IMF as well. These were a lot different, which we perhaps expected. We only show the downward pointing flux here. So that's pointing flux going into the ionosphere, because on average, you average out all the upward flux is essentially negligible, because that doesn't happen very often. And when it does happen, it's small in magnitude to the downward flux. So this is only showing upward fluxes. This, contrary to the neutral density, has a very strong IMF dependence, both in BY and BZ. For instance, it's a lot lower magnitude under BZ northward, and it's a lot higher under BZ southward. And then there's a very strong asymmetry between BY positive and negative too. In general, though, for all the patterns, we get enhancements in the traditional dawn and dusk return flow regions. And we get an enhancement around the cusp as well for all of them. So to see if we can pick out any correlation between the pointing flux and the perturbation density just in the cusp region, here we show latitude versus pointing flux for IMF, all the IMF orientations, but we only, so this is kind of like a keogram basically, but we only look at this region between 11 and 13 MLT, which is where we'd expect the cusp to be. So the red line or the red dots are the density perturbations, and the black dots are the pointing fluxes. Agreement is generally pretty good in where in latitude the pointing flux enhancement in the cusp coincides with the neutral density enhancement in the cusp. However, there are some discrepancies. For instance, the perturbation density is relatively similar, these red lines between BZ northward and BZ southward, but the pointing flux is way higher under southward IMF than it is under northward IMF. And this same almost anti-correlation happens between BY positive and BY negative, where there's higher pointing, there's a lower perturbation density for BY positive, but the pointing flux is basically the same between BY positive and BY negative. So there's inconsistencies with the magnitudes, but the location is pretty much the same where the enhancement is happening. So what we see is essentially the pointing flux on these fairly large scales, mesoscales on hundreds of kilometers, can't fully account for the density perturbations which are happening on the same scale of several hundred kilometers. So if I had to summarize it in like one thing, I'd say that the pointing fluxes don't quite equal the neutral density enhancements in the cusp region, but it's a lot more complicated than that. For instance, there's some things we haven't taken into account, for like we'd expect the pointing flux to change very quickly if there was a change in the IMF, which is given by like, the difference between BZ northward and BZ southward. They're extremely different because, when it changed, we'd expect maybe it to change on the order of tens of minutes. But the neutral density we know is a lot more slower to change to changes, in external forcing. So that's something we haven't really considered. Yeah, so there's a lot of nuances to this, which I haven't fully covered, but we have submitted to JGR Space Physics. It is under review currently, and I'll put the preprint in the. I'll put a link to the preprint in the chat box, so you can read that if you want to see a more detailed analysis, or feel free to send me an email as well.
Cool, thank you very much. We've got a question straight away from Mervyn Freeman, who asks, why is the cusp spot preferentially pre-noon MLT, i.e. not at noon for IMF BY approximately 0?
It's a really good question, because you'd maybe you'd almost suspect with co-rotation that it would be the other way around. Yeah, I'm not entirely sure about that. To be completely honest, it could have something to do with our processing and the fact that we haven't accounted for timescales like I've changed. Maybe we need to apply some kind of, but saying that as well, we have applied like a filter to like only do times where the IMF has been steady for a predefined period of time, to hopefully filter out times where the IMF would be variable and then the neutral density doesn't have like a chance to reach an equilibrium. But that didn't change our results, but it severely reduced the amount of data. So I'm not really sure the answer to that, basically. But it is interesting, but the BY symmetry is there, but and it seems to have a preference for the dawn side, but we're not entirely sure.
So Tom Sallard asks a naive question from the outer planets. Can you explain why the densities are enhanced by the increased pointing flux?
Yeah, it's basically just energy deposition from the pointing flux. The going thought is that's deposited at somewhere in the E region, and then that causes some kind of upwelling in the thermosphere, and then that pushes up to higher altitudes, and then the density is enhanced at higher altitudes. These are all F region, so not in the E region. Even though these are technically height integrated pointing fluxes, so they'd be of the entire ionosphere. Like most of this density enhancement is going on in the F region.
Okay, so Steve Milan asks, there's a consistent decrease in density post-noon or in the dusk sector at 80 degrees latitude. What do you think this is?
I guess you're referring to like this. Can you see my mouse pointer?
Yeah.
Yeah, I guess you're referring to this bit, right? I hope. I'm not sure.
He says you're right. Yes.
Okay. Yeah. So I think this is so above in the very high latitudes. I think this is basically due to the fact that when you go to very high latitudes, CHAMP is basically sweeping. The last 5 minutes of CHAMP could basically sweep a lot of different local times. So that could be some. I don't think this is terribly physical, and I think anything over like at the very extreme latitudes near the pole might be a bit suspect, just because like the way we've processed the CHAMP data might not account for like very high latitudes when the previous 5 minutes could have like gone over a. It can be very different depending on which direction CHAMP came from. So yeah, I hope I've explained that right. But basically, I think it's a bit of an artifact of just doing our processing at very high latitudes.
Okay, so just two more questions. One from Richard Horn, which asks, could you be averaging out the pointing flux fluctuations associated with the density enhancements?
Yeah, so like, yes, we could be averaging those out in two ways, both spatially and temporally. Spatially, because obviously our spatial scales are like hundreds of kilometers, when the fine scale pointing fluxes, which was seen by previous authors, are obviously much like on the order of tens of kilometers. And then temporally, because we're just averaging out all the data. So what this is basically telling us is that the mesoscale pointing flux isn't one-to-one with the mesoscale neutral density in the cusp region. So this could be a few different reasons. It could be either the difference between the two is telling us a lot about like those very fine scale processes and how much they contribute to the bigger picture, which is quite interesting. And what was it else? I had to respond to a reviewer in the exact same way, and I'm trying to remember what I said. It could also be an altitude thing, because like I said, I mentioned earlier, we're basically doing a height integration here, and most of the energy is being deposited in the E region, but we're not looking at densities in the E region. So it could be some kind of disconnect between that as well.
Okay. And then one final question from Colin Waters, who would have thought that energy input was electromagnetic and also particle precipitation. Do you think particle precipitation is dominant for your density maps?
I'm not sure. I haven't thought about that.
Fair enough.
There's no. Yeah, I'm really not sure about that. It could be.
Something to pick up after the meeting, perhaps. I will put you both in touch and you can chat about it after.
Yeah, it's definitely something to think about.
Thank you very much to Daniel. Next up, we have Jenny Carter, who is at the University of Leicester. So I'll ask her to unmute and share her screen.
Hello, can you see that coming up now?
Yes, yep.
So play show. Okay,
yep.
Should I just crack on?
Yes, yes, please do.
Cool. Brilliant. So today I'd like to speak about a small study that we have been undertaking looking at the evolution of height integrated conductances over the course of the substorm. So the graphic there is just to show an electrojet index as an example of a substorm. It's not one I've used here, but just to show onset and at the beginning of the expansion phase. So in the study, we've used the substorm onset list from the SuperMag dataset. And from that, we've used that to perform a superposed epoch analysis of height integrated conductances using bins with a size of a quarter of an hour. In part one of the study, we've investigated this behavior of the conductances over the course of an average substorm in general. And then in part two, which is ongoing, we're looking at splitting that by the magnetic latitude of onset. And we've done something similar with the Ampere field line current maps as well. Eventually, we want to compare these results with other statistical maps of conductance, but that's still to be done. So a word about where the conductance values come from. I have used the DMSP spacecraft to do this, and in particular the SUSE experiment on board the last couple of spacecraft that got launched. So the SUSE experiment has 5 spectral bands available to it. And so the DMSP spacecraft travels across the polar cap at about 800 kilometers altitude and looks down. And it takes about 20 minutes to do so. And it makes these sort of small strip scanning, if you can see that with my pointer. And it'll go over the polar cap every hour and a half or so. So from the 5 spectral bands, I'm interested in 2. We're interested in the Lyman-Birch-Hoffield long and short bands. There are some onboard and some post-processing steps that take place. There's an assumed atmospheric model and some cleaning up of that data for day glow and various noise sources. But afterwards, with a comparison between the long and the short wave bands and looking at yield curves, for example, we can get out these 2 parameters that are in the pinky purple boxes, a characteristic energy E and this mean energy flux Q. From these E and Q from the SUSE data, we have used the Robinson empirical relationship between those parameters, which you can see in the equations here, to estimate the height integrated Peterson conductance sigma P. And from this power law relationship, then we can make an estimate of the Hall conductance sigma H. So what I'm going to present now are some grids on a magnetic local time MLAT grids, where we have midnight to the bottom, and this is for the southern hemisphere only. That is because the DMSP spacecrafts, the way that they scan across the polar cap, they only take little strips. And so for the coverage that we have, we only get these maps of the southern hemisphere for the night side, which is the side that I'm interested in here. Here we have a grid that runs through the course of this substorm. So we start at 1 hour before a substorm and go to nearly 3 hours after substorm, with these labeled with the delta T's. So each row you can see that it's progressing through time. So we have these conductance maps in the purple maps with the orange grid lines on top. Underneath that, for the rows, we have difference maps. So this is just taking one particular time and comparing it to the previous time. So these are the greeny purple maps you see. Where we have a dark green area, we have a positive increase in the conductance, and purple would be a reduction in the conductance. So just to highlight 2 time points here, at substorm onset here, we see this increase in the main auroral bulge, where we're going green all the way around. But we're also seeing at higher latitudes, we see this really dark green area here. At half an hour after the onset, we see this high latitude area still in green, but we're seeing a lighter purple area kicking in. So this reduction in the conductances in the midnight area, but it's still increasing in the dawn and dusk sectors, and definitely at high latitudes. So it takes a while to calm down at these high latitudes and towards the extremes of the plot. So what we do then is we take MLT segments for a selection of MLTs running from 21 hours to 2 hours MLT segments. And we look at the behavior of the conductance, or the sum of those conductances over time. And also the parameters E and Q, the original parameters. So that gives us these 4 plots. So we have time along the x-axis in each case, and then we have the characteristic energy E naught here, the energy flux Q in this plot on the top right, and then the 2 conductance plots in the bottom. The colours here indicate the MLT sectors. So we can see after substorm onset at 0, we have this ramp up to the maximum values. And this happens between half an hour to 3/4 of an hour after onset. This is consistent with the literature. So this auroral bulge expansion associated with the expanding contracting polar cap model of substorm cycle. And we see this peak, we are seeing this peak in this orange and grey sector, which is an MLT of 23 hours to midnight. And that's for both these E and Q, and then this is reflected down in the conductances. What we aren't seeing is an eastward expansion. So in previous work in the literature, there was a strong eastward expansion of the auroral bulge, where with auroral data from both PolarVis and ImageWick showed the auroral bulge quickly moving eastwards. And if we're not seeing that in this data set, where we'd see MLT sectors such as 1 and 2 moving, excuse me, the peak moving quickly eastward within these plots. But we do have much cruder time steps than were available to those image and PolarVis data sets. So that was part 1. That was just sort of a general substorm behavior for the conductances. And in part 2, we went and looked at that Superman substorm list again. So there's about 17,000 substorms that went into this, and we've made a split in latitude. So the histogram on the top left shows the vertical dash lines are where we've made the splits. They're fairly crude, and they were just to get a decent amount of contributing SUSY data sets to go into each bin. So we have this below 63 degrees And then in these smaller 2-degree steps up to anything above 71 degrees. When I plotted on the top right, when I plotted out the substorm list with the onsets based on the latitude and the local time, we can see that there was quite a few onsets that occurred on the day side. I've ignored those for now and just taken the night side onsets for this study. So I've done something similar than we did with the DMSP SUSY data, and binned up the ampere field line current maps on this superposed epoch basis. So this is the time series that you see here for an example set for Southern Hemisphere for one of those latitude bins for the onsets. And here we use the convention that upwards current is red and blue is down. So this runs from just 1 hour before the substorm up until 3 hours afterwards. It's hard to see, but there's sort of suggestion of the expansion of that polar cap around here, though it's quite subtle. And then if I do something similar to what we did before, but only looking at one particular MLT wedge, this is between 4 hours and 5 hours MLT, and plot the mean current density over time, we have these two plots here, one on the left for the upwards current and on the right for the downwards current. This time the colours here are representative of the latitude bin of the substorm onset. One thing to note here is we seem to see this split between lower latitude bins up here in the blue and the purple traces compared to the others which have lower current densities in the, say, we're just looking at the upwards ones for now. We can also see that the lower latitude substorms have a fairly flat profile throughout the substorm with a slight increase of substorm onset, but it's not, for this mean value, it's not particularly remarkable. The higher magnitude seen for lower latitude onset is consistent with work, say, that John has done, and we're seeing these higher magnitudes for the field line currents at lower latitudes. We can now do plots that are similar to our work before. And so we have the conductance maps here and the purpley maps, but this time I've overplotted the field line current contours on top and the blue and the red. So unfortunately the blue cyan color doesn't come out wonderfully well on this, but you can see that we run from 1 hour before the substorm to 3 hours afterwards. And again, we have this difference map in the blue, the green and the purple maps. And you can see this time at substorm onset, everything's kicking off at substorm onset in this great increase. And then we start to reduce again at about 3/4 of an hour afterwards. And this is just for one of those example latitude bins, 63 to 65 degrees. So similarly as we did before, this time the graphs are flipped and we have the current, the conductances, on the top, the Hall and the Peterson conductances on the top versus time, and the characteristic energy and the energy flux on the bottom. And these are mean values for a sector that goes from 21 hours ML2 to 2 hours MLT. This time, again, the colors are, the key is down here. And we can see that we have this ordering in latitude, whereby we have the highest values for the lower latitude substorm onsets, as we'd expect from previous work. And there is some suggestion here that the lower latitude, I've highlighted this in the red box, but there could be that this lower latitude bins are peaking slightly less, if we sort of draw a line between them here, slightly less than those higher latitude substorms. But this is, we're still investigating this behavior. So in summary, I just wanted to sort of point out that although these are height integrated conductances, the bonus of using ampere and SUSY together gives us this simultaneous large-scale spatial regions that that detailed measurements of conductances that are height resolved can't give us. So if we can do some pinning down of this method, then this will hopefully be useful for climate work, for example. We are seeing these peaks in the conductance scene about half an hour onset in this 23 hours MLT sector. There are some assumptions that I haven't gone into here, but there could be differences in how we calculate the conductances based on whether we're looking at discrete or diffuse aurora. Now, we think that our assumptions at the moment are reasonable given that the input energies of the precipitating particles. We think we're seeing this two population split with the conductances, with this lower latitude conductances really being different to the higher latitude. So it was around 63 degrees where we saw this split. Now, this could be related to phenomena that we've seen before. For example, Steve Milan has a paper talking about convection breaking at lower latitudes due to increased friction for these lower latitudes substorms. And we would like to verify these SUSY conductances using, say, for example, IceCat-derived values for a bit of ground truthing of those values. And we're in the process of working on this and writing it up simultaneously. So that's me. Thank you.
Thank you very much, Jenny. If there are any questions for Jenny, we've got one from Martin already. How variable in duration are the different phases of the substorms? He's just wondering if a time normalized superposed epoch analysis by phase might be helpful.
Yes, Martin, it would be helpful, because if you, we did see, and we commented this on the original paper, that the values at the end of the time period we chose, up to about 3 hours after the substorm, it didn't quite recover to the pre-substorm levels. So substorms can have a range of periodicities. So that might be some of the issues of what we're seeing that's different. So yes, I think there it would be worthwhile investigating some normalization there. Thank you.
So Sandra recommends that Jesper Gerloff has a nice method to normalize on a single epoch. And there's also the Forsyth et al. 2015 SOFI method that splits things by phase. So they might be good follow-ups to Martin's question.
Yes, Jesper's a co-author, so I need to chat more, I think.
Right. I don't see any other questions. So I think people can run away for coffee. Thank you very much, Jenny. There will be more chances for discussion later in the meeting, especially in the poster session. But if anyone has any questions for Jenny and she's not around, let me know and I can relay them on to her and put you in touch. Okay, so we will be reconvening at noon with a talk from Martin Archer, and Rob Shaw will be chairing that second session. So we will see you all in 10 minutes time. Thank you very much.
Okay, welcome back everyone. So it's 12 o'clock and we're going to continue with a talk by Martin Archer on the wide-reaching impacts of magnetosphere surface waves. So Martin, if you could like to share your screen. And
okay,
thank you.
Hopefully you can see that and you can hear me okay. Right, yes, so I'm talking about magnetosphere surface waves. I'll start out with a bit of a reminder for everyone of system scale MHD waves in the magnetosphere. Basically, because of the magnetosphere's structure and the different sort of boundaries within it, then all of the different MHD wave modes can form sorts of resonances within the system. So, I mean, the most well studied are the field line resonances that come about from Alfvén waves, and we can see an example of that here, of a resonating magnetic field line, which is bounded by the ionosphere due to its high conductance. Also, there's been known for many decades is the fast magnetosonic waves bouncing between boundaries such as the magnetopores and the plasma pores can form these so-called cavity or waveguide modes shown in green, and those two constitute body waves in MHD. But of course, we have these discontinuities, and they're highly dynamic as well. And so they have surface waves. And I would say the most studied example of that is the magnetopores down the flanks, where you have a velocity shear on both sides of the boundary, and therefore waves grow out of the Kelvin-Helmholtz instability, which can then radiate into the magnetosphere. But also, of course, you can have pressure-driven waves by the upstream variations in the solar wind, which can not only cause the day side to move, but also the flanks. And I would say that mostly these surface waves have been studied in the flanks, where the Doppler effect of the magnetosheath flow is more dominant than the natural frequency of the discontinuity itself. But it is thought to have its own natural frequency, and we call this a surface eigenmode. And that's the natural response of the discontinuity. And it's usually thought of in terms of when you impulsively drive it, say by like a shock wave or a pressure pulse in the solar wind. And these have been kind of formulated both for the magnetopores, but also for the plasma pores in simple sort of box model type setups in MHD, because they can give you some insight into what's going on. This is an animation of that setup for the magnetopores, where we have our black magnetopores here, and because of bounding by the ionospheres in the northern and southern hemispheres, we can form this standing wave like so of the magnetopore surface, and its signature within the magnetosphere is that of an evanescent fast magnetosonic wave that can actually penetrate quite deeply within. So actually the eigenmodes for both the magnetopores and the plasmapores have only recently been discovered in observational data. And here's the example for the magnetopores in a study that we did a couple of years ago, which showed that when you impact the magnetopores with a very strong and isolated pulse, in this case a magnetosheath jet, then you get damped oscillations at a very well-defined frequency of the boundary itself, and then the corresponding ULF waves, which were able to confirm the signatures that we expected from theory. However, there is something of a conundrum here, in that we would expect on the magnetopores that these surface waves get vectored tailward by the magnetosheath flow. And so it raises the question of how these waves can actually get trapped in a local position and form a resonance at a given spacecraft location, away from the noon meridian, where of course that flow is negligible. And actually the observations were taken in the mid to late morning sector, and there wasn't any evidence that the boundary perturbations were being advected tailward, despite the flow speeds being non-negligible, about 140 kilometers a second. And similarly, if you go to global MHD simulations of this phenomena, this seems to suggest that these near standing type waves should span almost the entirety of the dayside magnetopores. And so that calls into question how this is even possible, and if it does have a set scale, where does that scale come from? And so I'm going to try to kind of solve these by looking at energy propagation using both observations, simulations, and theory. And a key concept is going to be Poynting's theorem for MHD waves, which you can basically form as the rate of change of an energy density, and this is the energy density of the wave perturbations themselves, which have a kinetic and magnetic component, must balance with the divergence of the wave's energy flux, which in a medium with no background flow is simply the Poynting flux, like so, of the perturbations in the electric and magnetic field. But if you have a medium with a background flow, then also that wave energy is going to get advected by that background flow. And so you can think of that as an extra energy flux given by the wave energy density multiplied by that flow speed. And the key concept is that of the energy velocity, which is the velocity at which the wave energy is actually traveling. And the way you can get that out is by taking a ratio of a time averaged energy flux, in our case, the Poynting flux, and take the ratio of that to the wave energy density. And in the case of completely stable waves, then that would be absolutely equivalent to group velocity. So we'll first briefly look at the Themis observations. I'm just going to show a time series here from Themis E. So we've extracted out the wave perturbations in the magnetic field. Is the velocity here, which contributes obviously to the energy density in the kinetic sense, and the electric field. And take these are all in field aligned coordinates, by the way. So blue are radially outwards. Red is azimuthal, going in the usual sense, and then the yellows are along the local field line. If we look at the pointing vector here, and particularly the time average version, which is by the thicker lines like so, we can see that that they are pointing, or at least at MSE, it's pointing towards the subsolar point, so against that usual tailward direction that we'd expect for ULF waves. There also seems to be some radially outward component and a field aligned component like so. And we can actually see the directions for all of the different spacecraft here. So this is in the XY plane. We can see they're all pointing towards the subsolar point in the XY plane, which is against the typical expectations you get for surface waves further down the flanks, where they travel tailward and actually they radiate energy into the magnetosphere. So if we calculate this energy velocity though, so we take the ratio of the pointing vector to the energy density, then looking at this azimuthal component, it seems very comparable to the actual measured magnetosheath flow by the furthest out spacecraft, Themis B, when it was outside of the magnetopause. And so that seems to suggest that these waves are propagating against the flow and forming an azimuthally stationary wave. So we want to test this hypothesis, because this is a quite intricate data analysis to do with spacecraft, to look at that in more globally with an MHD simulation by essentially hitting the magnetosphere with a pressure pulse and seeing its response. So I'm just going to play a movie here which shows the changes in the compressional component of the magnetic field in response to such a pulse. So we can see the pulse is coming in like so. We get a whole wash of directly driven transient activity, and now you can see starting to form these standing waves where we've got anti-phase either side of the magnetopause boundary, but then further down the flanks we are seeing propagating waves as well at the same sort of frequency. I'll just play that one more time. So it seems that we have a sort of standing behavior and a propagating behavior from this response, and we can look at that a bit more quantitatively. So the graph here looks at the displacement of the magnetopause at all the different local times, and we can see that there's basically three things that happen. So firstly, you get a strong compression of the magnetopause when the pulse arrives. It then rebounds and overshoots, and then it undergoes these damped oscillations like so. And actually, there are two frequencies involved. So there's a primary frequency at 1.4 megahertz. That's present at all at local time. So it originates on the day side, but we can see it at every single local time. That's 1.4 megahertz. That corresponds to the surface eigenmode frequency here. But interestingly, there's a secondary mode that only emerges further down the tail. It varies its frequency with local time, and that seems to be the intrinsic Kelvin-Helmholtz waves that you would normally study. The interesting thing is that both modes actually grow in amplitude down the flank. So actually, you're having this surface eigenmode, which originates on the day side. It's seeding waves, which are then subsequently being grown by Kelvin-Helmholtz, even though they're not at the peak of the instability. They're at a lower frequency, but the Kelvin-Helmholtz can still amplify those waves. And if we look at the propagation of these waves, you can see that in a region between 9 and 15 hours of local time, the phase fronts are vertical. And we've done this more quantitatively as well to show that there is seemingly no azimuthal propagation within this region. Whereas outside of that, then we recover the usual tailward propagation in both flanks. So we can look at that and test our hypothesis from before by looking at the time average energy fluxes associated with these waves. So we look at a map of the pointing flux like so, and we can see that across the day side, we see the pointing flux within the magnetosphere is, again, pointing towards the subsolar point and not tailward. The tailward direction emerges past the terminator, essentially. If we look at the advective flux, that's exactly what you'd expect. It's mostly the magnetosheath flow like so. And therefore the total, if we add the two together, then we can see this picture where we have counteracting fluxes on either side of the magnetopause, whereas the pointing flux is directed towards the subsolar point, and then outside in the magnetosheath, it goes tailward. And what we can do is we construct these maps at every local time in the magnetopause, look at the energy flux tangential to the magnetopause boundary and construct these maps like so, and then integrate them along the normal direction on both sides. And we can see that the two exactly balance approximately between 9 and 15 hours MLT. And beyond that, it seems that even though the Poynting flux is trying to kind of go against that advective nature of the magnetosheath flow, it loses out ultimately, and therefore we start to recover the usual tailward propagation in this region. But why is it this region? Why is it 9 to 15 and not some slightly other region? Well, for that, we've just gone to very simple MHD theory. In those box models I was showing you before, you can just construct the energy velocity of a surface wave, the net energy velocity, set it to 0, and then see what condition that imposes on the wave. And essentially, you construct your energy velocity like so. That gives you this condition on the strength of the magnetosheath flow for this situation where you have no overall azimuthal energy flow to be possible. But if you combine this condition with the surface wave dispersion relation, that tells you, what the magnetosheath flow has to be relative to the solar wind flow, and it's actually a ratio of the square root of the densities. And if you then look at a model of magnetosheath properties, that is satisfied for exactly the same region that we were talking about when you look at a Spreiter model, and we'd expect the variability of this region actually to be pretty small. So for most cases, we'd expect it 9 and 15 hours MLT, you should be able to have azimuthally stationary surface waves of the magnetopause. So the theory is in excellent agreement with our MHD simulation. And so our conclusion can be summarized basically in this cartoon. If you have an impulsive and broadband pressure pulse, which could be a magnetosheath jet like we had in the observations, a pressure pulse or a shock, basically because of the finite scale of the field lines and bounding by the ionosphere, your K parallel is going to be fixed. However, there's no, because you've got a broadband pulse, it's not at a well-defined frequency, you're going to excite a range of K5s. And so looking at what happens to that range of K5s will depend on which regime you're in. If you're in a small magnetosheath flow, yes, you'll lose some energy down tail, particularly for the ones that are directed that way, but there will be a K vector that exactly opposes the effective effect, and therefore you can trap your energy locally and have a standing surface wave, an azimuthally stationary wave. Whereas when the flow gets too large, then the flow is going to dominate and you only get this resultant flow down tail. However, this also tells us how we're able to see these fluctuations, which can then subsequently go via Kelvin-Helmholtz. So this is a really global response that you get out at a well-defined frequency when you impulsively drive the system. Thank you.
Thanks, Martin, for that interesting talk. If anyone has any questions, please put them in the chat or the Q&A. Otherwise, I will jump in. I was wondering how long the damping period is, these waves.
Yeah, so we expect them to be strongly damped, actually. And there's different values depending. So it's quite strongly damped in the MHD simulation. It should be a function of the thickness of the magnetopause. In an MHD simulation, you've got a very thick magnetopause, but it's actually numerical dissipation that dominates. But actually, we typically imagine there only to be a handful of wave periods for this. But the interesting thing is that because you're able to see some fluctuations, the Kelvin-Helmholtz instability that kicks in down the flanks actually means that you get waves lasting for more periods than you do at the day side. So actually, they could be more persistent in the flanks than they are where they originate.
And just quickly, in case anyone else has any other questions, do they drive a voltage on the magnetopause? Would they have an impact sort of inside the system?
Yeah, so you should be getting like field aligned currents out from them. What those signatures are and how they direct energy into the ionosphere, that's something that's still not very well understood, because it's a different response to an alphenic response, and that's something that I'm hoping to look at next.
Okay, we do have one question from Eric Priest. Why does Poynting flux point towards sunward?
Yeah, that's a good question. I didn't actually go into detail in the talk. It actually comes from the damped nature of the waves. So if you take the magnetosonic dispersion relation and you put in a complex frequency with the sense that it's being damped, the result is that you should actually be losing energy out through the magnetopause. In opposite to Kelvin-Helmholtz, where if you're unstable and you're growing the waves, then that's why you radiate the energy in. In a damped case, it's the opposite.
Okay, thanks. So if there are any further questions for Martin, please follow through in the Q&A on the chat, and I think Martin will respond to them there. Otherwise, we'll move on with our talk from Andrei Samsonov. So Andrei, if you could unmute and share your screen, please.
Hello.
Hello. We can't see your screen yet, no.
Thank you. Good afternoon. In our work, we study geosynchronous magnetopause crossings and the magnetospheric consequences such as magnetic storms and substorms. At the beginning, what is geosynchronous magnetopause crossing, or GMC? The geosynchronous orbit is a circular orbit at a distance of 6.6 RE from the Earth.
Andrei, we still can't see your screen.
Ah, sorry.
That's good. Thank you.
Thank you. Geosynchronous orbit is a circular orbit at a distance of 6.6 RE from the Earth. And usually the magnetopause is located farther from the Earth than 6.6 RE. Only occasionally during strong compressions, day-side magnetopause may come closer to the Earth, and spacecraft at geosynchronous orbit will make magnetopause crossings. Our goals are determine solving conditions during geosynchronous magnetopause crossings and find which of the events are caused by interplanetary coronal mass injections, stream interface regions or gravitational interface regions, and interplanetary shocks, and study geomagnetic activity after GMC. How can we achieve the goals? First, we use the empirical magnetopause model of Lin et al. To make list of GMC events. We could make a list of events using in situ observations of geosynchronous spacecraft, but then we would miss many events because only the spacecraft located near the substorm point can observe GMCs. On the contrary, if we use an empirical model with the solving parameters from monitor NEO1, we will get a nearly complete list of GMC events. We may miss a few events or add a few excess events, but in general, we get the right list. Second, we use hourly average data and select 24 intervals after first GMC crossings. If the model predict a GMC event, then we consider 24 hours after the GMC as one event. And we may get several GMCs during the 24-hour intervals. Third, we use ICME, SIR, and IP shock catalogs to find solving drivers for GMC events. We study the distribution of solving parameters during GMCs and also study geomagnetic activity after GMCs. This slide shows the empirical model makes a good job in predicting of the GMC event. This is an example with 3 successive GMCs related to 3 ICMEs. The left figure shows the solving parameters and the magnetopause end of distance predicted by the model. Dashed threaded line on this panel indicate the distance of 6.6 RE, and red arrows mark GMC events. The bottom panel shows the magnetospheric indices. Each of the strong magnetospheric compressions nearly coincide with increase in IE index up to 1000 or 10 tests or more. But only the last event results in a severe magnetic storm. The right figure shows GOES observations and geosynchronous orbit. Looking at BZ component, we can say that the second and third events are certainly GMC observed by GOES. And in the first event, we see magnetic field fluctuations, but BZ keeps positive. But if you look at GOES position, we will see that both GOES are close to the substorm point in the second and third events, but near the terminator plane or on the night side in the first event. So this is the reason why both GOES don't see a GMC in the first event. This slide show the number of GMC events rise during the two last solar cycles. We collect totally 99 events, and the figure shows sunspot numbers, the total number of GMC hours, the number of ICMEs with certain criteria, and the number of hours with extreme DST and SME indices. And you can see the number of GMC in general reproduce the solar cycle, but not perfectly well. The next slide show solving conditions for event. The panel displays the density, velocity, BZ, and electric field EY. Color lines show temporal variations in 99 events, and the thick black line shows the averages. Let me compare the behavior of the density and velocity. The average density has a clear maximum at t equal to 0. Here, t0 is the time of the first GMC. In each particular case, the density maximum may occur at t0 or a few hours later, but in general, the density decreases at the end, to the end of the interval. On the contrary, the average velocity increases before t0 and then keeps nearly constant. In each case, the velocity maximum may occur at any time within the next 24 hours. And the bottom panels show BZ and EY. The average BZ has a minimum and EY has a maximum at t0. And the average BZ and EY approach 0 a few hours later. But they may be both strongly positive and negative in each particular case. This slide shows the distribution of solving parameters at t0. Red vertical line indicates the average over the whole interval, not only GMCs. The density in the GMC events is always higher than the average and often higher than 20 particles in a cubic. And the velocity is mostly higher than the average, but rarely extremely high. And as expected, BZ is mostly negative and EY is positive. The next slide shows the magnetopause standoff distance and indices of magnetospheric activity in the same format as the solving parameters before. I'll skip details and only mention the time lags for the averages. The minimum of average standoff distance occurs at t0, and the extreme of average PC, SML, SMU, and KP indices occur 1 hour later. And the time lag for the DST index is on average 8 hours. These are the distribution of minimal SML and maximal SMU indices, and we search whether the nearest local extremum on left panels, or highest extremum in the next 24 hours on right panels. I emphasize the 2 points here. First, the SML modulus in many cases is near or higher than 1000 nanotesla. And second, the time lag of the extremum for both distribution are small, with the peak whether at 0 or 1 hour. The same as before for the DST index. You can see that the DST minimum only in 15 cases is above minus 50 nanotesla, and in more than half cases it's below 100 minus 100 nanotesla. And the time lags are variable. The highest probability is 3 hours, but the average is 8 hours. Finally, we compare the solving conditions on left panel and magnetospheric conditions on right panel for the ICME related and SIR related events. The average solving dynamic pressure is about the same for ICME and SIR events. However, the profiles of the average density and velocity are different. At T0, the density is higher for SIR events, but the velocity is higher for ICME events. And the velocity remains high for the ICME events, and it grows within next 5-10 hours for the SIR events. And the magnetospheric activity in terms of DST and SML indices is high for ICME events. We know from the literature that ICMEs often result in stronger magnetic storms and higher auroral activity than those caused by SIR. So we suggest that the explanation may be the different behavior of the solving velocity and density shown here. This table shows average parameters at T0 for ICME and SIR events, and this number emphasizes the results shown on the previous slide. The higher average velocity for ICME and the higher density for SIR. Both the DST and SML indices drop stronger for ICME than for SIR. So I come to conclusion. We classify 74 of 99 GMC events as associated with ICMEs, 18 events as associated with SIR, and 76 events as associated with IP shocks. All the GMCs are connected at least with one of these solvent sources. The GMC events are mostly followed by severe substorms and moderate or strong magnetic storms in the next 24 hours. The dynamic pressure pulse at the first GMC mostly results from a strong enhancement of the density, and IMF-BZ is negative at T0 in most cases, but may vary between large and negative positive value in each particular case. The average PC, SML, SMU, and KP index reach extrema in 1 hour after 0 time, while the average DST index reaches a smooth minimum in 5-8 hours. We obtain the same time lags between the first GMC and minimum of DST and SML for strong magnetic storms and strong substorms, as for the whole database. And we compare solar wind at magnetospheric conditions for the GMCs related to ICMEs and SIRs. And the SIR events are characterized by higher solar wind density, while the ICME events are characterized by high velocity. And the ICME events on average results in stronger magnetospheric activity in terms of DST and SML indices than SIR events. Thank you. I finished.
Thank you, Andrew. I actually had a question about whether you thought the preconditioning of the magnetosphere by previous solar wind events was more important than the solar wind shock type to give you a GMC, but you have actually already answered that in the conclusion, so you're way ahead of me there. We're a bit late on time, actually, so if there are no other questions in the Q&A, I can't see any. I think we'll just move on to the next talk, which is by Sandra Chapman. So, Andrew, if you could stop sharing your screen, and if Sandra could share hers, that'd be good.
Okay, so let's see. Oh, could the other person remove their slides? Great, okay, share screen. Where is it? It is, okay. Okay, hopefully you can see something.
Yeah, we can. Thanks, Sandra.
Brilliant, okay, so thanks for the talk slot, and what I'm going to do is talk about a paper that Lauren, myself and Karen Began have just sent off to space with it, and I think it's on archive as well. And it's about using networks. I'll remind everybody the sort of things we were doing with networks to say something about something hopefully practical, okay, about what the effects of large storms are on the UK power grid. Okay, so just to remind people, what is the point of these networks? What kind of thing can we get out of this method for looking at data? So the problem is, as you'll have been seeing through all these talks, we all have these lovely pictures with lots of data on them, and we're trying to look at lots and lots of data and lots of times, and can we kind of condense this information somehow? So if, for example, if you have supermag, you know, here's just a snapshot of the onset of a substorm, and here are all the nice little vectors, the 90-degree rotated field directions. And so you've got the magnetic field at all these points, and what you can do is ask for the cross correlation between all of them. Okay, so window Fourier cross correlation, and if that exceeds a threshold, I can draw lines between those guys, and that gives me the thing on the right, which is a network. And then you can say, well, that looks like a mess. I can do lots of things with it. One is I can just color code it in. So the green is everything at high latitude, and the blue is everything at low latitude, and the red is the thing connecting between. So you can see how correlated, spatially correlated features are moving around. Okay, so you can just look at it, and that's the first thing you can do. But then you can parameterize it. So the long-term goal of this is, I can't keep looking at these movies and pictures, okay? I've got to put a number on it. So this is an example of what we did. It's done something very recent we've just published. And you can say, okay, I want to know how clumpy it is. And this is an idea, this is a network parameter now. So network sites, there are lots of these things that are already, you know, off the shelf for us to use in a sense. So we've got to think about it a little bit, okay? And so with community structure, you say, if I want to visit my friend, okay, if my friend is living in the same town, there are lots of different ways to get to my friend. But if my friend is in the next city, I have to go along the motorway. There's only one or two ways to get there. And so I can count the number of paths. And this tells me whether, you know, the magnetometer stations or whatever it is I'm looking at are all in a community. And so we can then get a number that tells us, is this spatial field made up of one big correlated patch or lots of small ones? And that's this parameter modularity. So then you could do statistical things. So this is a plot against time of lots and lots of substorms. They've all been normalized using Jesper's pattern method, okay? So you can calculate across all these storms and say, well, what happens to this parameter? And you can see it goes from high to low, saying I start off going from lots of little patches to kind of one big one. So now I can look at the behavior of lots of events. So this is the power of networks. And then, well, that's quite useful to know, because then you can say, well, what do the models predict? And if the models only ever predict lots of small things, like these kind of flow bursts, and they never predict a big thing, then you know that can't be right. Whereas models that predict the formation of one big current system are consistent with the data, not just one or a few events, but you can statistically look at lots of events. So there's a whole machinery around networks that we can use to answer different questions. So having just given that flavor, I want to turn to the problem I want to talk about now, which is what happens when a big storm hits the UK power grid, okay? So think of the problem in the following way. The input is the observed magnetic field as a function of time across a bunch of points. And the output is the response of the grid. And so what we've got as input, we've got magnetometers. And I'll start by showing what you get from, looking over Europe, and then we'll zone in on the UK. You can then feed that into a model which contains the ground conductivity and the structure, the physical structure of the grid, and then make your network on the grid itself and ask, well, what's happening to the currents flowing in the grid and how are they correlated? So that's what we're going to do, okay? Okay, so to break this up into pieces. So first of all, let's just think about how we're going to do the cross correlation. Now, when I was showing you the things before, looking at magnetometers and substorms, we use Fourier canonical cross correlation because we had vectors, and you've got quite a lot of different stuff going on. So, okay, standard thing, Fourier decomposition. I do cross correlation between the time series. But now we know we want to look at dB by dt. We're interested in sharp changes in dB by dt. So instead of doing Fourier, I'm going to use Haar wavelets. Again, this is still complete and orthogonal, so I'm decomposing the data without throwing anything away. Okay, and what the Haar is, it's just a step function. Okay, so think it's a bit like doing a kind of a, sweeping across the data and comparing it with the step function. That's kind of what you're doing. And then you're varying the scale of the step function. The different wavelets varies the scale, increases the scale by a factor of 2 each time. So I'm asking for, the sharpest change, and then the next sharpest. And so what this plot is showing, the top, I'm just looking at the magnetic field, and you can see where it goes blue, that's when it goes really negative. So you can see the onset here. This is the 2003 storm. So we've picked a big guy to look at, okay. Here the thing starts, and you can see lots of things going on. So the blue is when there's the biggest BN. And then these are the first 3 Haar wavelet decompositions. And you can see, so this is the highest, sharpest time resolution, next sharpest. And so you can see this is the power in each of these. And you can show quite readily that this power actually is just telling you what dB by dt is. So the units of this thing is the units of dB by dt, calculated on different time scales, okay? So the shortest one is just on the time scale of the data, and then twice, 4 times, or whatever. So this is the thing we're going to work with, and you can see it picks out all the sharp changes in the time series. Okay, and the thing we're going to do, we're going to plug this in, or look at the effect of this on the power grid. So this is the second part of the problem. So just to show how it works, just to kind of test it, we're going to drive the model of the power grid with a model, a very simple electric jet model. And this electric jet model, it's really simple, okay, just to see what happens to the network. So it's basically like a Cusp envelope, okay, in latitude, and it's uniform in longitude. So it's like this yellow bar, and it moves sharply. So it's in Scotland, and then it moves to the middle, and then it moves to the bottom. And you can see here, if I look at the GICs, and if I look at the wavelet power, you can see there's this Cusp thing, which is smoothly varying in time, over Scotland, and then it goes over the middle of the country, and then at lower latitude south of England. So it sharply jumps between them. And so then we go to the power grid, the model of the power grid, which includes the ground conductivity and what the power grid response is, and ask for the wavelet cross correlation between points on the power grid. And that's what's being shown on the right here. And it's pretty much a mess, okay? The blue are the lines between, so the network connections. The little circles are how many connections each node has. And the color is the wavelet power, okay? And this model, you can see it's completely correlated. It's completely uniform. So all it does is kind of light up the network. When it's over Scotland, all of Scotland is pretty much correlated. When it's over Middle England, all the middle's pretty much correlated. And when it's over the south, all the south is pretty much correlated. So it's doing what you'd expect. So this is just a check of what happens when you drive the model. So now what we're going to do is put these two things together to take the actual data as input, the 2003 storm, and drive the UK power grid. And that's what we're showing here. And these are just 4 snapshots because the thing's doing all sorts of stuff in time. Okay, so this is at the onset and then some later times. And you can see all sorts of stuff goes on, okay? First of all, it's highly intermittent. These patterns I'm showing you don't dwell for a long time. It's minutes, few minutes. I'll show that again in a minute. You can see there are very long range connections, okay? You can get connections right across from north to south and shorter ones as well. If you look at the circles, the size of the circle is the number of connections each node has, how connected in it is, how correlated it is with others. The color is the power. So you can see you get a big circle and the power is not so big. The purple is strongest and yellow is kind of weaker. Okay, so you know, once you've got a dB by dt, the amount of connectedness, you know, how correlated you are, is just not proportional to the power, not directly proportional. More interesting than that. The other thing you can see is not all the nodes are connected. This thing is full of nodes, but certain nodes, and they're not local to each other, but there are certain nodes like to be connected. So they form kind of supernodes, like a club. Some of these you can see pick out these kind of horizontal lines. These are the 400 kV lines going across the grid. Sometimes these, you can see these clearly being picked out in terms of these long range correlations. Sometimes it's not. So, you know, there's a lot of real interesting detail here. So I say this is looking at this particular storm. We've looked at a few other big storms as well. Basically, you get a lot of detail. But just to stress, this is the coherent response of the grid. I'm not saying this is current flow on the grid, okay? This is what is correlated with what. And so this is the kind of stuff you get out of this. Okay. To try and put numbers on this, I mean, if you look at these plots, you think, okay, great. You can count, I'll just pop back here. We can count the number of connections that go from north to south or north to middle. We can count the number of connections that go within each region, okay, as a function of time. And that's what I'm plotting here. So you normalize it to the total number of connections available, or look at the absolute number, which is plotted on the right. And you can see it's really intermittent. This is the point. So how the grid is responding is changing all over the place, okay, which is really interesting. You can ask, well, how much of this is kind of really long range, say between north and south compared to within north? And usually, okay, the numbers are quite small. The top 3 panels, which are showing within regions, the normalized number is going up, scale is going up to 0.4. These bottom ones, the normalized scale is going up to 0.2. So you can just see by the amplitude of the things, sometimes they're of order, and sometimes the long range connections, there's kind of half as many as the short range ones. But as I say, very intermittent. The little lines are the snapshots that I showed you, but you said there's a lot of other stuff going on here as well. So it's really interesting. The other thing is the sort of connectivity we're seeing. These long range connections are not just the physical connections on the grid. So, you know, if you think what the grid looks like, there's lots of short range connections. So we're not just following the sort of pattern, the physical pattern of the grid itself. Okay, so finally, we can count, well, what's the likelihood if I sit on a node, you know, how many connections does that node have? And then I can make a histogram of that, okay? And that's what these are. Each of the panels are the 4 snapshots. And of course, you can see they're changing all over the place because the networks themselves were changing. So this is the probability of being connected. So if you're within the north, middle, south, or whatever, and then between, you can see they're kind of varying. But the main character to notice is you often get these really narrow distributions. In other words, there'll be a particular degree, there'll be a bunch of nodes which have, say, 50 connections, and all 50 have 50 connections. And what that is a community of supernodes, that 50 nodes are all friends with each other and they are ignoring everybody else. So if you're in the club, you know everybody else who's in the club, and if you're out of the club, you don't know anybody. So there are these kind of supernode connections that set themselves up that are really correlated. And it's not just a spatial thing, because they'll be quite spread out in space, and within them there'll be nodes that aren't connected at all. And this is all, again, highly variable. Okay, so just to kind of summarize all that, I'm really kind of plugging, you know, thinking about new ways to look at data. I mean, it's quite striking. I mean, today, but you know, last time I was able to walk around the posters at AGU, I noticed this poster after poster of maps. People wanted to explain something. They had to show sort of a whole stack of these maps because it's changing with time, whatever it is. And then they wanted, that was just one event. And then they want to show another event. And how is it different? They want to show 50 events. So we want to think of a way that we can capture this spatial temporal information and compare it across many events. This is kind of what this is about. And networks are a way of doing this. They don't rely on mapping onto a regular grid. Things could be moving around, you know, like with the Earth's turning, you know, that's why I was asking about Ampere earlier. It doesn't matter if they're moving around. And the key is you calculate a cross-correlation matrix between all your observing points and you threshold it. There's a lot of detail in how you might do that. Okay, and so one application, we could say, okay, well, let's look at what a real physical grid is doing, the national grid. And we find some really interesting things. You get these long-range connections, you get communities of supernodes, which are really strongly connected to each other, correlated, but quite spatially distributed. Okay, it isn't just following the dB by dt, but of course you need a certain dB by dt. It isn't just following the physical connectivity of the grid, because the grid itself is exponential distributed. People have looked at physical networks and physical grids a lot, okay? And so it's a way of characterizing, well, you know, vulnerabilities on the grid, which parts will be connected to others in terms of these big events. So I say, this is just a kind of first cut, and I'm sure there's a lot more one can do on this to try and quantify what's happening, you know, with the grid response to a storm. Thank you.
Thanks, Sandra. Very interesting talk. Yeah, I agree that it's important. Oh, one second, I was going to find something that Martin Archer has a question. Do the networks characterize the largest features present? Can they handle superpositions of different modes too?
It's not the large. It's absolutely not the largest features. It's not amplitude. This is a really good question. This is really important. It's correlation. It's whether one point is doing the same as the other. Okay, so I always give an example. You know, if you're looking, say you've got boats in a harbour and you know, buoys and things, and their wave comes along, you can't see the wave. You can just see the boats. The boats will bob up and down. It's not the amplitude. It's the fact that they're all bobbing up and down. It's that they're correlated. And that's how you know it's one wave. If it was just amplitude, you know, just the individual amplitudes, it could be a whole bunch of different waves that were incoherent. So it's looking for coherent, propagation of coherent information. And that's really why it's nice, because it can pick out, you know, these kind of correlations between things. And then maybe that can have some kind of predictive value that if you know something's going to happen over here, it's going to do it over there as well.
Okay, thanks. I do have questions actually, but we're running a bit close on time, so I think I'll find you in the poster session and ask them there.
All right.
Thanks, Sandra. Okay then, so our next talk is by Graziella Brandolini-Raymond, and she is going to be talking about these SMILE missions. So you could share your screen, please. Okay, thank you.
Can you see it?
Yeah.
Good. Okay, sorry. So thanks for giving me the opportunity of talking about SMILE, the Solar Wind Magnetosphere Ionosphere Link Explorer, which fits very well with the theme of this meeting. SMILE offers a new and global way to explore solar terrestrial relationships. It's a joint space mission from start to finish by the European Space Agency and the Chinese Academy of Sciences. Is under development and is due for launch at the end of 2024. Now, the structure, the dynamics of the magnetosphere are thought to be mainly controlled by magnetic reconnection, which takes place between the magnetic field carried by the solar wind and the terrestrial one, and allows plasma from the solar wind to penetrate the magnetosphere. So the basic theory of magnetospheric circulation is pretty well known. In fact, it's illustrated at the top of the slide by the cartoon that shows the progression of the Danji cycle. And it has been explored by many spacecraft that have made in situ measurements on the micro scale. In actual fact, this interaction is complex and takes place on a global scale, which still is not very well understood, as well as its evolution. So what are the scientific motivation of SMILE? Well, SMILE can answer questions that will help to distinguish the various modes of the interaction I've been talking about, and the characteristics of the magnetic reconnection, what drives to geomagnetic substorms and CME storms. And essentially, SMILE will contribute to answering the question, what drives space weather, which is so relevant to the consequences that space weather has on our technological infrastructures. And so the questions that we are trying to answer are like, where is reconnection of different characters like steady, transient, bursty? What does it depend on? Only solar wind parameters or something else? What drives the substorm cycle? Again, properties of the solar wind, or maybe seasonal effects, and what causes the CME-driven storms? Are they, for instance, sequence of some storms? So this slide tells you about what SMILE is going to do really. Well, SMILE is a scientific mission which will investigate this dynamic response of the Earth magnetosphere to the impact of the solar wind in a way that has never been tried before and is global, as I said. So imagine a CME that impacts on the magnetosphere, and for favorable conditions of the orientation of the magnetic field in the solar wind and the terrestrial one, you have penetration of plasma from the solar wind into the magnetosheet. And now we know that there we have X-rays produced by the process of solar wind charge exchange, which takes place between the highly charged ions of the solar wind and the neutrals of the Earth exosphere. So SMILE, which you see up there over the magnetosphere, is carrying a soft X-ray imager that will take maps of the X-rays produced in the magnetosheets and the cusps as well. Now, the final end of fate of the particles that come in from the solar wind is that of precipitating down to the poles of the Earth and producing the aurora. So SMILE will also carry a UV imager that will monitor continuously the northern aurora. In addition to that, SMILE also carries in situ measurement instrumentation, which will tell us the conditions of the solar wind and the magnetosheet plasma while it's flying. And SMILE is going to do all of this from a highly elliptical northern polar orbit, which you see there sketched, and which takes it out to some 19 Earth radii. I've got a couple of slides now showing you images of where we have got to with building SMILE. Here you see images of the soft X-ray imager. First of all, in the center is an exploded view, a CAD design of the telescope. And the X-rays come from the top, they go down to the micropore optic, which lays under the baffle that eliminates stray light from the sun and from the bright Earth. The micropore optic gives us the opportunity of having a large field of view for a low mass. It's essentially a lobster eye type of optic. And then the X-rays then go through, are focused down to the focal plane, where there are two large format CCDs, which give us images as well as spectra of the focused X-rays. On the left-hand side, you see a photograph of the primary structure of the SXI. This is, in fact, the structural thermal model, which is undergoing tests as we speak. And on the right-hand side is a test camera, with mounted in it one of these large format CCDs. And the PI of SXI is Steve Sembe from the University of Leicester. The UV imager is a telescope with 4 mirrors in it, and it will give us pictures of the northern aurora with high spatial and temporal resolution. You see at the bottom a sketch of the inner workings of the telescope. The UV band pass, which is pretty narrow, is achieved by coating both the optical surfaces and the detectors appropriately so that we avoid as much as possible visible light contamination. On the left-hand side, you see some photos again of, at the top, the optics module, the breadboard, and at the bottom, the engineering model of the electronics. And then we have the in situ instrument package, which is responsibility of China. Well, I should have said the PI of the UVI is Eric Donovan from the University of Calgary. Now, these are the in situ instruments, which are, as I said, responsibility of our Chinese colleagues. One is the light ion analyzer, a top hat analyzer for protons and alpha particles that measures density, velocity, temperature. And you see a photograph of the engineering model on the left-hand side. And then we have the magnetometer, a flux gate type, which incorporates 2 sensors mounted on a 3-meter boom. And the bottom image on the right-hand side shows a deployment test that the boom is undergoing. Now, turning to the SXI imaging analysis. Now, there are several people in our SMILE consortium that are working at preparing for the analysis of the images that SXI will provide. And in practice, what they are doing at the moment is to simulate X-ray emissivity and then SXI images, starting from given solar wind conditions, and from there simulating the observed count maps that we will be obtaining from SXI. So we start from MHD simulations that give us model X-ray emissivity in 3D in practice, what is shown on the right-hand side here. And then the detectable X-ray emission is calculated by integrating along the line of sight from SMILE, you see up there over the cube. And so by doing that, we create 2D maps of the emissivity. And you see an example of this at the bottom on the left-hand side. And that's an MHD simulation for particular solar wind conditions. Now, on the basis of that, we can use these simulations to go through the SXI simulator to produce then the expected count maps. And you see an example in the middle of the slide. Now, Andrei Samsonov has done some work looking at particular cases for different solar wind conditions. And in particular, I'll show you a couple of things he has done. One is, case one is an artificial stationary case for the parameters that you see there. And he has then used a Bathurst MHD simulation to produce the 2D map that you see at the bottom left-hand side. And this is for a position of SMILE practically at apogee. Now, previous work has shown that the maximum emissivity corresponds to the tangent to the magnetopause. Oh, my slides have a life of their own. And so what he has been looking at is the location of the maximum emissivity along the line between the Earth and the Sun. And so what you see there in white is the maximum emissivity location, and in black is the polynomial fit to that line. And he has done that for both the actual MHD simulation and the counts map that you see on the right-hand side. In addition to this, he has also tried different techniques to determine the magnetopause position, which is what we are looking for. We want, with SXI images, we want to determine the location of the boundaries of the magnetosphere. And what you see here at the bottom on the left-hand side is a diagram showing the profiles that Andre has obtained by using in blue the electron current density, in red the density gradient, and then in black the dashed line represents the integrated emissivity through the MHD simulation, and in the continuous line is instead what you get from the count maps. On the left, we use only single pixel, and on the right-hand side, the count maps has been averaged over 5 pixels, so the continuous line is smoother. And what you see at the top is a table summarizing the locations or the standard distance of the magnetopause for the various techniques that Andre has tried. And essentially, they are all consistent within a fraction of an array. And he has applied the same techniques on case 2, which is an actual event that took place in 2012 due to an ICME that Jenny Carter has studied already, and had extremely high solar wind density and northward IMF. And again, you see here in white the location of the maximum emission, and in black the polynomial fit. In this case, on the left-hand side of the simulation, MHD simulation, you actually see the blob that corresponds to the cusp as well, but that doesn't appear in the image from SXI on the right-hand side because it's out of the field of view. Now, again, here we have the profiles as I have described before, and the summary of the measurements for the standoff distance that Andre has derived. And as you can see here, the numbers are much smaller than in the artificial case, because this is a case of a particular strong compression that the magnetosphere was subjected to. And finally, the conclusion is the impact that the SMILE will have. On one side, from an astrophysicist point of view, it's very interesting that SMILE turns X-rays from the magnetosphere that have always been an unwanted background for the X-ray observations of cosmic sources when the line of sight goes through the magnetosheath, and SMILE turns them into a diagnostic tool of Sun-Earth relationships. SMILE will provide a scientific input to studies of space weather, and especially because it will provide this data, the remote sensing data that will validate all the global models that I have shown you around examples of already, of the interactions between the solar wind and the magnetosphere. Now, SMILE has also got a strong potential for outreach because it will make images, movies, that will captivate the public, especially for a science, that of the Earth's magnetic field, which has been invisible so far. And the cooperation with China is also an interesting aspect of this project, and of course is building on the experience that ESA already had on Double Star. And that's the end of my talk. Thank you for listening.
Thank you, Graziella, for a very interesting talk. We have one Q&A from Eric Priest, who says, how far down the flanks will you see X-rays, and what will be the spatial resolution of X-rays and UV?
Okay, well, down the flanks, I'm afraid we won't be able to see much at all, because the density of the neutrals and will be very low, so there won't be solar wind charge exchange emissivity. As far as resolution, now in terms of the X-rays, we have probably a 1 degree resolution of the instrument that corresponds to 0.5 on an RE, depending on where you are in the orbit, of course. And the resolution of the UV imager is 100 kilometers.
Okay, thank you. Joe Borowski did have a question in the chat, but I think it's been pretty comprehensively answered by Jenny Carter. So unless there are any further questions, I think yeah, I'll say that will bring our session to a close. So just got some groundkeeping stuff to say. So lunch is now going to be for half an hour, but feel free to join the gather time links that I think John Coxon will be sending around. If you decide to stay in Zoom, then please mute and turn off your video, otherwise gather time won't work properly. Poster presenters, please beat your posters by 13:30. Just like to say that Alexander Fogg's poster will be presented by Katrina Jackman. We reconvene in Zoom at 14:30.
Okay, so my computer says it is now 2:30, so we're going to start our last speaking session of the day. And to begin with, Steve Milan's going to talk to us about dual lobe reconnection and horse collar auroras. So if you could go ahead when you're ready, please.
Okay, thank you, Sarah. Hopefully you can see my slides here. I'm talking about horse collar auroras. This is an auroral phenomenon that's been known about for quite a long time. I think it became evident in the 1980s when spaceborne auroral cameras were first deployed, that during quiet geomagnetic conditions, the auroral oval could transform from its usual configuration, which I'm showing on the left here, to the configuration that you see on the right here, where the dawn and dusk regions of the polar cap seem to become filled with weak auroras and often cusp aligned arcs as well. This auroral phenomenon was given the name the horse collar auroras. For those of you who didn't have a rural upbringing, I've just indicated some horse collars on the bottom right there, just so you can see why they were given their name. So spoiler alert, we think these are due to dual lobe reconnection. This is not a new idea by any stretch of the imagination, but what we're talking about in today is how this configuration evolves, or how the auroral oval evolves into this configuration. So here I'm just reprising the reconnection geometries that are available at the magnetopause. When the IMF is directed southwards, then we get subsolar reconnection, where closed field lines are opened. And if you look in the ionosphere, you should see anti-sunward flows in an expanding polar cap, as first proposed, well, as proposed in its final state by Cowley and Lockwood in 1992. If the IMF turns northwards, but you have a significant BY component, then reconnection now moves to either the northern or the southern hemisphere, or an individual IMF field line can reconnect in the north or the south. Here, the reconnection is with already open field lines, and so you don't actually create any open field lines, nor close any, and so the polar cap size remains constant, but the flux within the polar cap is stirred. Now, if the IMF points directly northwards, then the same IMF field line is thought to be able to reconnect in both northern and southern hemispheres. And now you're going to take open flux and you're actually going to close it. Now, around the mid-2000s, several people speculated about what the ionospheric signatures of this might be. And both Chisholm and Imber suggested you'd effectively get the reverse of the Cowley and Lockwood picture for southward IMF. And people did go and look for this signature, but perhaps with limited success. What we're proposing today is that rather than the closed flux, which is coming out of the dayside polar cap boundary, rather than being distributed symmetrically to all local times, as the Chisholm and Imber picture would suggest, we're saying that that flux actually hangs around near the dayside and slowly moves around towards the flanks. And so you get your normal reverse twin cell lobe convection cell kind of picture. But the open flux and the closed flux evolve in the way that I'm indicating on the right there. So this closed flux is distributed to dawn and dusk, and you get a progressive closure of the polar cap. And it's within these new regions of closed flux, we think that you're getting the horse collar auroras. So the signature that we should be looking for here is, if this picture is actually correct, you get a progressive motion of the polar cap to this teardrop shape. There should be anti-sunward flows within the open polar cap, the remaining open portion of the polar cap, and anti-sunward flows within the regions where you've got new closed flux. And it's interesting to point out that if this process continues long enough, you might expect the polar cap to close entirely. So here are some observations showing an interval when we think this is occurring. So I've got 3 rows of panels here corresponding to 3 passes of DMSP over the northern or the southern regions. The panels on the left show the northern and southern field line currents as measured by ampere. And then you can see in one of those 2 panels, you've got the track of the DMSP spacecraft as it moves over, and the ionospheric flows as measured by the drift meter instrument on DMSP. And then on the right, you've got the auroras as measured by the DMSP SUSY instrument at 2 different wavelengths. And the IMF conditions are shown on the bottom here. The times of the DMSP passes are indicated by the 3 vertical green lines there. So in the first row, then we've got northward IMF, but with a significant BY component. And if you look at the ionospheric flows as measured by DMSP, then you've got flows that are consistent with just lobe stirring in this case. And note that the polar cap is still nice and open at this time. Then in the second panel, the IMF is pointing almost due northwards. It's a little bit more difficult to see on the DMSP track here, but there is actually sunward flow in the central polar cap region, and there are 2 regions of anti-sunward flows to either side of that as well. Notice also there's a lovely NBZ current system as measured by ampere at this time. It's much more prominent in the southern hemisphere than it is in the northern hemisphere, because the southern hemisphere is the summer hemisphere in this case, and so there's a lot of conductance to carry these currents. And hopefully you can see in the auroras at this time that you're beginning to get the hint that the dawn and dusk sectors of the auroral oval are moving polewards, and you're beginning to get the formation of this teardrop shape for the polar cap. And then later on, the IMF has been pointing almost directly northwards for an hour and a half thereabouts. At this time, you can see in the bottom panel that the IMF around about the times of passes D and E here has been almost purely northwards for almost 2 hours. You've got now very clear sunward flows in the central polar cap and very clear anti-sunward flows to either side of that. Again, the NBZ current system is measured by ampere, and you can see that the formation of the horse collar auroras is well progressed at this stage. And I should note, though I don't show it here, that as this interval continues, then we think the polar cap becomes entirely closed after a while. Okay, so that's all very nice. Why am I talking about this in a system level science session? Because I think this has quite profound consequences for the magnetosphere. If you look at where this newly closed flux is mapping to, I'm showing my take on where this is in both the Z is equal to 0 plane and the X is equal to 0 plane, the bottom left and right here. And this closed flux, first of all, starts off just near the dayside portion of the magnetopause, but it becomes entrained inside the magnetopause and moves around the flanks of the magnetosphere. And this is where you often see the NBZ low latitude boundary layer. And so this is captured solar wind plasma. We think this is a very efficient method of catching solar wind plasma, and it's known during these periods of purely northward IMF, if the situation continues for long enough, then the plasma sheet can increase in density tenfold, what's known as a cold dense plasma sheet, because of this capture of the solar wind. If you look at it from the sides as well, you can see the mapping of the horse collar auroras that we're observing in the ionosphere with the low latitude boundary layer. They should be magnetically conjugate to each other. So this should be a very efficient solar wind capture mechanism. And we think by watching the development of these auroras, we can actually track where in the magnetosphere this newly captured plasma resides. So one of the next things that we want to do is actually use in situ data to go and look at the development of these auroras and to see whether we can see the solar wind plasma as well. Just going to go back one slide very quickly here. So this sort of development of the auroras actually turns out to be very common. So Gemma Bauer, who is now following up on this work and is doing a statistical survey of the occurrence of this phenomenon, she's looked at about 7 years worth of data now, and she'd found 80 clear events a year pretty much. And I was quite surprised at how often it occurs. IMBA suggested that this dual lobe reconnection should only really occur for clock angles less than about 10 degrees. But it turns out this occurs about 4% of the time. That may not sound like very much, but it's actually an hour a day. So it's a pretty common phenomenon. Okay, this purely north of IMF is not going to occur forever. Eventually the IMF will change orientation. What happens if it does? So you start with a teardrop shaped polar cap as in panel A here. If you then turn the IMF southwards, then you're going to append new open flux to the day side portion of the polar cap, and you'll create perhaps a mushroom shaped polar cap like I'm showing in panel B. If there's a significant BY component to the IMF, then that open flux will be preferentially added at dawn or dusk, and the rest of the flux within the polar regions will be stirred around. And sorry, that's the number 44 bus going past there. And if the IMF remains northwards, but you get a BY component, you can begin to speculate about what might happen there. So these observations are not new. Lots of people have reported them in the past, though I think we've got the first time understanding what's going on here. Here's some observations from Kumnock and Blomberg from 2004, showing the formation of horse collar auroras and then the evolution of the arcs afterwards. And they've even got some DMSP tracks on here as well. And I'd just like to superimpose these two panels here, showing that it fits really quite well with the sorts of patterns that we're suggesting here. Okay, so to conclude, we think that dual lobe reconnection can form the characteristic NBZ morphology of horse collar auroras, and this is linked to the formation of closed magnetic flux at high latitudes in the dawn and dusk sectors. And then you can speculate about what happens afterwards and how the auroral configuration will evolve. And we're currently speculating about the source of the cusp-aligned arcs that you often see associated with these horse collar auroras. Perhaps most interestingly, these auroras should be directly related to solar wind capture in the NBZ low latitude boundary layer, and perhaps the formation of a cold dense plasma sheet. And perhaps by tracking the formation of these auroras, we can see where in the magnetosphere this plasma has got to. I'd just like to end with, this could be an interesting target for observations by SMILE, both with SXI and UVI. You can use UVI to look at these auroras, and SXI maybe to peer inside the magnetosphere, not just look at the magnetosheath emissions, but maybe there'll be emissions from the dense plasma captured within the magnetosphere that you can look at as well. Okay, thank you very much.
Okay, thanks for that. That was really interesting. Just looking at the chat, doesn't look like anyone has posted any questions.
That was clearly very clear.
I liked some of your diagrams. I thought they're really helpful in understanding it. So there are still no questions coming up. If you want to catch Steve later or post him any later messages, we'll just move on now to Lauren Orr, who will be talking to us about the comparison of high latitude electric field models. So if you could share your screen, Lauren.
Is that shared?
Yeah, I can see it. So please go ahead whenever you're ready.
Wonderful. Cool. So I'm going to talk to you today about comparison of high latitude electric field models. So this is very much ongoing work. So if I ask more questions than I answer, I apologise. But this part of the Swimmer project, I'm going to explain sort of the wider, where it fits into that. And then I'm going to go more into some comparison and ways to standardise input variables to these models. So I'll start off with a very broad Swimmer and what it is. So Swimmer is Space Weather Instrumentation Measurement Modelling and Risk project. So it's got very high objectives that cover everything from satellite and aviation operations to electric power distribution. So we fit into that as the Hemisphere part. So the aim of this is to seek to secure a step change in the Met Office's ability to specify and forecast the Hemisphere. And to do this, they're using a model called a NES. This is one of their diagram or one of their videos from the website of a NES. So a NES stands for Advanced Ensemble Electron Density System, a simulation system, and it's a 4D data assimilation model. So this is built on empirical electric field climatology models and has been built at Birmingham. So what we want to do is see if we use more modern or near real-time data models, will this improve its output? Will this improve its ability to nowcast and forecast? So to do that, we want to do a rigorous comparison of state-of-the-art high-latitude electric field models and see how they differ and kind of what one's better, but that's kind of hard. So let's see if we can move away from this weird YouTube. So to do this, we are going to look at these models. So the ones that ANES is currently using is Weimer and Helios, which are empirical electric field climatology models based on spacecraft data. So Weimer is from 2005 and Helios is originally 1982. So we want to see if we start to include new models like Thomson-Shepard 2018, which is based on SuperDARN data, and eventually look at Bass's EOF model and Lancaster's TD model and see, do these improve the output? So to do this, we're going to first look at Thomson-Shepard and compare it to Helios and Weimer. And we're going to try and do this quantitatively. So we hit a snag pretty quickly because Helios's input to the model is very different to the other two. So to compare things, it's very nice to put in the same output and put in the same input and see what the output is. But we've already got a problem. So Weimer and Thomson-Shepard are quite easy to compare because we've got BY and BZ IMF conditions, we've got solar wind conditions and tilt angle. So they're directly comparable straight away with the same inputs. But we need to try and do something with Helios because its input is cross-polar cap potential, which is the output for Weimer and Thomson-Shepard. So we've tried to find some equations that we can link these variables or even other variables to cross-polar cap potential so we can compare these things. So we found a couple of equations to link IMF and solar wind variables to cross-polar cap potential. We've got the Boyle equation from 1997, and we've got Milan's equation from 2012, which is actually for day-side reconnection, but we're going to use it as a proxy to see how it goes. We've also got some other equations that link omnivariables, so we can use these for real storm events and compare how the omnivariables change. So at a certain time, we can see what the polar cap index is, and we can link it through this seasonal relationship to cross-polar cap potential. And there's another equation using KP, which is actually what ANES is currently using. So we can see how this one compares to the other equations. So here we have plotted
these cross-polar cap proxies for the 2017 September storm. So this isn't even using the Helix model yet, because obviously it's the input, not the output. But we've compared these inputs to the output from the Thomson-Shepard and the Weimer model. And yeah, you can see there's a lot of change. So we've got a scale of 0 to 500 here. So they all are reasonably similar during moderate conditions, but there's a lot of change within these high extreme conditions, which is understandable given there'll be a lot less data going into these equations and data sets at extreme conditions. So we can see there are IMF-derived equations have very high extremes during the peak of the storm. We can see that the Thomson-Shepard model, this blue line, is very low consistently, which is quite common with super-Darn-derived things. So yeah, this is quite low, and then we've got some in the middle, but are they right, are they wrong, who knows? So this is the thing, we don't have a baseline, we don't have a right answer to compare things to, so we can just see how they compare. So yeah, we can also compare these equations with increasing IMF magnitude. So here I've just plotted IMF magnitude times the solar wind velocity and see how cross-polar cap potential increases as this increases. So we've got the Boyle and Milan equations for IMF conditions, and we've got the Weimer and Thomson-Shepard output. You can see there's a lot of differences between all of them. We have big differences between the outputs for each. So this is color represent clock angle. So our clock angles are coming out quite different depending on what the model used is. So the dashed lines are Thomson-Shepard and the solid are Weimer. So example, here's a red one, which is BY positive, BZ negative, and here's the corresponding Thomson-Shepard. So there's big differences in the values, in the magnitude, but also in the structure. So for our IMF equations, we have very linear relationships, which is understandable. That is what goes into the equation, so that is what comes out, but that's not what our models are showing. So there's, for example, our BY positive is different to our BY negative, whereas they're the same here. So, but currently we haven't even used the Helix model yet. We're still just comparing inputs to outputs of other models. So we'll look at some convection maps. So here we have convection map for some moderate conditions. So we've got BY positive 5, BZ negative 5, and moderate solar wind conditions. And the corresponding value for the cross-polar cap potential from the Milan equation would be about 55. So we've put that into our Helix equation, and these are our outputs. So we can see there's big differences between all of them. So Thomson-Shepard has a consistent Hartner-Maynard boundary, about 55 degrees. Weimer's is slightly offset from the center. Helix doesn't have one, it instead has a convection reversal boundary, and beyond that things decrease exponentially. Other differences include Helix has a defined zero potential line, which is solely dependent on BY. So we'll investigate this a little bit later. And we've got the Helix model directly input what percentage of the cross-polar cap potential the max and the min will be, which is quite different from our Thomson-Shepard and Weimer models. So again, we can see differences, but we can't compare them empirically. And where we can try and compare them is with difference maps. So I've just minus one from the other. But this is kind of hard to understand. It's hard to interpret, because if we think about the boundary could change, then that could change everything. So if the boundary, lower latitude boundary for the Weimer and the Thomson-Shepard model were the same, would this map be the same? We don't know. And it's also, there's different maps for every input, so it's very hard to compare this. So we'll move on and look at storm. So this is 2017 September storm. We're about here in the storm, so we've got consistent negative IMF for a while, so we can see our maps are quite consistent. And about 10 past now, it's going to go mad because it just drops. So I think our equations for the input cross-polar cap potential are way too high to be realistic, but our rotation should still be consistent. We can see that the Weimar has also grown a lot, but Thomson-Shepard has sort of saturated. It's reached its peak sort of values and never really exceeds these. Yeah, and this has went down to a lot lower latitudes. So we've got comparisons, again, very hard to do empirically. So we can start to look at some parameters. So here we have, I mentioned before that the Helix model directly defines what the minimum potential and maximum potential will be as a percentage of the cross-polar cap potential. So we've just got that percentage here. So it is 56% of the cross-polar cap potential consistently, and we're going to compare that to BY, and unsurprisingly Helix does not change as its input. So we want to see how does this compare to the other models. Is that a good assumption? And we can see that they're very different. Thomson-Shepard and Weimar both seem to have a BY dependence. So as BY gets more negative, our minimum becomes a smaller percentage of the total cross-polar cap potential. There also seems to be a BZ dependence, which is our color. They seem to line up quite nicely in different or BY values. So there's probably a BY BZ dependence or potential, which is not really surprising. But Helix is not showing this. So this is just one type of thing that Helix may be missing. So yeah. So I've still got lots of questions. I've not really answered what is the best model, which would be the ideal outcome, but how do you decide what the best model is? We want to see which one's the most correct, but we need to find something really, what do you compare it to? So we're trying to figure out which little bits are different and what seems more correct, but it's still very much ongoing work. And also, are our assumptions valid during these extreme conditions? Data sets are going to have a lot more data at moderate conditions. So are the extremes just not really well covered? And of course, that's the bits that the Met Office or space weather people are going to be interested in. So it would be good if they're decent. So what's next? We want to compare this to the TV, the Lancaster model, and the BAS EOF model. So we're currently working on that, but we're not quite there yet. But yeah, we want to see how they compare as well. So yeah, that's me.
Thank you, Lauren. I don't know if people are writing questions at the moment. There aren't any there, so I'm just going to start off with one of mine. I think it relates to one of your outstanding questions, actually, about how do you decide what is most correct. So I was wondering in these models whether you're more interested in trying to get like the amplitude or the min-max potential right, or the orientation of the geometry and where the different patches are in your convection plots.
Yeah, so we've been trying to do a bit of both. I feel like the total potential would be a really good factor, but given that it's the input to Helix, it's quite hard to compare it. So we have been doing that one, but yeah, then you're actually comparing different equations instead of the actual model. But yeah, we're also trying to look into, so Helix has very defined equations that define all the little bits to it. So we're trying to compare them to the other models. So for example, my last law in comparing the potential of the minimum and the maximum to different variables. Other things like, yeah, I've looked at where the max location, the minimum locations are compared within the models. Other things would be where the zero potential line is, but that's quite complicated because it's straight in the Helix model, but it's very wibbly in the other ones. So yeah, where do you compare it? So yeah, these are all sorts of things we're working on.
that's quite a long list. Good luck working out how to quantify all of them and working out which one's the most important. If anyone does have any further questions, feel free to unmute yourself and ask one now. We've got a minute or so. No? Okay, in which case, next we have our last speaker for the day, Joe Borowski, who will be talking to us about a system science approach to solar wind magnetosphere coupling. So whenever you're ready, please.
Great. Rob, do you want to run the slides or shall I try it?
If you want to, then you'll have control over them, but I can if you need to.
I'll go ahead and give it a shot here. Does everybody see that?
I can see you. So whenever you're ready, please go ahead.
So this is some system science tools we've been building to look at solar wind magnetosphere coupling. And Mick and I started this when Mick was at Lancaster University and I was a visiting faculty there. So typically when you sort of look at solar wind data and compare it with magnetospheric data, you typically measure the magnetosphere's reaction to the solar wind by one number, typically like the AE index or the KP index or something. But from a system science point of view, we know that a lot of things happen at once in the magnetosphere. So we'd like to look at a state vector of the magnetosphere that accounts for a lot of different things that are happening. And we're going to do the same thing with the solar wind. We're going to build a solar wind state vector, and then we're going to look at correlations between the magnetospheric time-dependent state vector and the solar wind time-dependent state vector. So in a sense, we're going to broaden the description of the system away from the one variable thing, but then we're going to recompact the description and take projections of those state vectors into scalars. Good, so here's to set the stage. This is a single variable description of the magnetosphere. This is 17 years of data. Every black point is 1 hour of data. Vertically, we're plotting the AE index. Horizontally, we're plotting VBZ of the solar wind driver function. And so we look at this plot and we can say a few things. We get a correlation of 57%. It's a very poor correlation. So it's a weak correlation. So if we look at 1 minus the correlation coefficient squared, we get 67%. And that means that 67% of the AE index variability is not described by the variability of VBZ of the solar wind. The blue curve is a 50-point running average of the black points, and the red curve is a linear regression fit. And so you can see the blue curve and the red curve look very different. And so it's not a very linear response that we're looking at of the magnetosphere to the solar wind. So when you're trying to do these calculations, these correlations or any other data analysis of comparing solar wind data with the magnetosphere's reaction to the solar wind by some sort of measured reaction, you find there's a few things that are always problematic. One is that all solar wind variables have strong intercorrelations with each other. So the variables are carrying a lot of the same information as each other. There's noise in the data. There's noise in the solar wind data, mostly because the solar wind that hits a monitor at L1 is not the same solar wind that hits the Earth. And the magnetosphere is a high Reynolds number system, so there's a lot of noise in its data too. It's really not reproducible. If you did something exactly the same, the magnetosphere, if you tried to drive it the same, the magnetosphere can have different reactions. And point number 3 here, there's a lot going on simultaneously. There's a lot of physical processes that act to drive the magnetosphere from the solar wind. There's reconnection, viscous interaction, there's Mach number effects. And there's multiple reactions of the Earth's magnetosphere to the solar wind. You know, when you drive it, convection increases, you get aurora, you get all kinds of current systems, plasma heating and whatnot. So there's a lot going on. So we want to go with this systems approach. So we're going to explore vector correlations where we have the magnetospheric state vector, and we're going to correlate that with the solar wind state vector. And it turns out it overcomes a lot of these problems that have been bothering these kind of studies. It likes the fact that there's intercorrelations in the solar wind variables. It's going to exploit that. It's really good, since we have multiple measures, it's really good at reducing the noise. And the fact that there's a lot going on simultaneously, we're actually going to try to account for that. So let's go ahead and do it. So for today, we're going to create a 9-variable, time-dependent Earth state vector, E of t. And the 9 variables that go into that for the 9 dimensions are the first 6 listed here are different geomagnetic indices, which measure different things going on in the magnetosphere. Number 7 and 8 are the global power of electron and ion precipitation into the atmosphere as measured by DMSP. And number 9 is a multi-satellite measure of the pressure of the ion plasma sheet at geosynchronous orbit. So for the 8-variable state vector we're going to use today for the solar wind, S of t, the first 6 variables here are pretty standard variables that you would grab from the solar wind to describe how the Earth reacts to it. Number 7 is the angle of the IMF from radial. So it's kind of like the BX component of the solar wind. And number 8 is what you'd call the amplitude of turbulence in the solar wind. It's the upstream vector fluctuations of the magnetic field, the amplitude of those. Okay. So to do the correlations, we're going to use something called canonical correlation analysis. And canonical correlation analysis looks for correlation patterns between 2 sets of variables. Like one set of variables are the variables of the Earth in the Earth vector, and the other set of variables are the variables of the solar wind in the solar wind state vector. And CCA will take those vectors and make projections of those vectors that are scalars. So it'll give you a set of, take the Earth vector and give you a set of Earth variables, E1, E2, E3. I don't know if my pointer works, I guess not. Oh yeah, here. That are projections of E. And then it'll also, accompanying those E1, E2, E3, it'll create matching variables from the solar wind, S1, S2, and S3. That are scalars, time-dependent scalars. Okay, and they have some correlation properties which we aren't interested in today because we're only going to look at E1 and S1, the first 2 variables that come out. But each of these E variables, these scalars, represent different reactions of the Earth system to the solar wind. We're only going to look at the first one though, and we're going to take hourly average data from 17 years. So here's a plot of what we get. This is a plot vertically of the composite Earth scalar E1 vertically versus horizontally the composite driver variable scalar from the solar wind S1. And every black point is 1 hour of data. The correlation coefficient we get here between the Earth and the solar wind is 92%, which is really high. When you play these games of correlating the solar wind and the Earth, it's almost impossible to hit 80%, and here we've hit 92%. The red curve is a 50-point running average of the black points, and the blue line is a linear regression fit, and notice how the red running average tracks the line. It's a very linear response we're seeing between the Earth and the solar wind here. So the correlation coefficient of 92%, 1 minus the correlation coefficient squared is 15%. So only 15% of the Earth variable is not described by knowing what the value of the solar wind variable is. Okay. And it says over on the right-hand side, robust, and I want to explain what that is because it's really important. If this answer that you get when you create these variables, you get a robust answer. So if we take only data when geomagnetic activity is low, let's say low KP data, and derive these variables, and then we test these variables on data where geomagnetic activity is high, we get an excellent answer, excellent description. If we only take low speed solar wind times to derive this, and we test it on high-speed solar wind times, we get an excellent answer, excellent description. If we only derive this at solar minimum and test it at solar maximum, it's excellent. So we keep getting the same answer for how to derive the variable S from the solar wind and how to derive the variable E from the Earth. We get the same answer no matter which subset of data we take. We're getting some sort of a universal thing that's going on. We don't fully understand it, but we're very fortunate to have it. Here's an example of the robustness. This is the plot of that data again, and then in that data we have marked out in different colors 5 superstorms that went on during this time interval. And you can see how the data from the superstorms is very well described by this answer you get from using all the data. Okay, so to summarize, what are the advantages of this state vector approach? Okay, so we're thinking about global behavior and global reaction to the solar wind. So number one, it accounts for multiple aspects of the state of the magnetosphere, ionosphere, thermosphere system. The projected variable follows the behavior of the solar wind more directly. Number three, can't read it. I have something over top of it, so you have to read number 3 yourself. Number 4, relation of the magnetosphere to the solar wind is linear in this description. The same fit applies, number 5, for strong driving as for weak driving. The same fit applies throughout the solar cycle. Same fit also applies low speed solar wind versus high speed solar wind. Number 7, I didn't talk about, but in today's talk, but this methodology uncovers independent modes of reaction of the Earth to the solar wind. And we only looked at the first mode where all the geomagnetic indices go up together or come down together. There are other modes where some indices go up and some go down in intensity. And it's really interesting to look at those. And number 8 is, I think, really important. This is this robustness again. Because we can train on low activity data and it gives us a really good answer for testing on high activity data, what we think is that predictions that we make may be accurate for as yet unseen extreme solar wind conditions. Like if we have a Carrington solar wind, we may be able to predict the Earth's reaction pretty well to that. And that's all I wanted to say today, so I'll stop.
Thanks, Joe. So I've got a couple of questions. I don't know if there are any yet in the chat. Yep, here's one. So would you be able to give us an example of an independent mode of reaction?
Yeah, there's 2 that we've been looking at. One is where the high latitude indices go up as the convection indices go down. So it's like AE goes up while KP goes down. And opposite also happens. And another one that we see, and we can tell in the solar wind what's driving it, and as I remember, it's a combination of the speed of the solar wind versus the clock angle favorability, and that controls that mode. And the second mode is ion precipitation goes up and electron precipitation goes down and vice versa. And that's a density of the solar wind versus clock angle thing.
So we've had a further question. Steve Milan asks whether you can give us some insights into what E1 or S1 are.
We have formulas for them, and E1 is it's a linear combination of those 9 variables that goes into the Earth vector, and S1 is a linear combination of the 8 variables that went in the solar wind vector. And it's kind of an arbitrary thing. Some people like to gauge the magnetosphere by DST, and they know, okay, large DST means this, small DST means that. And other people like me use KP, low KP, high KP. We have a feeling for events. I think you could just take this variable E1, which we're going to derive a standardized one, and just learn to like E1 and just learn to describe all your stuff by E1, you know, low E1, high E1, you know, you'll know what it means. And it's a much better variable to use in a sense, because it's so predictable from the solar wind.
Have you had any opportunity to look into how E1 or S1 are made from the state vectors and see if they correspond to any particular physical processes or like common states of the magnetosphere?
We haven't tried to analyze that. No.
Fair enough. So it looks like I have time to ask some of my questions.
Make them easy.
Oh dear. Oh, there's another one first. Have you considered the effect of the reconfiguration timescale of the magnetosphere? So it would be interesting to see if the CCA modes change if you use different time lags.
The time lag question is easy. What I showed today, there's no time lag between the solar wind at Earth and the Earth reaction. We have a paper, Rick and I, where or I think it's maybe just me, where we put in variable time lags for all the variables. We allow them to vary, and we randomly kick them to optimize things. So we sort of, and the time lags are almost change the answer by nothing. It will give you maybe 0.5% better correlation coefficient, and the time lags are pretty modest. They're typically 1 hour-ish. So we've tried that, and I forget what the first half of that question was. Have I tried something else? Or?
I think one of the reasons why Rob was asking about the timescale was to see about time lag was because of how long it takes for the magnetosphere to reconfigure. So that was the first half of the question.
Yeah, but now see what this answer that we're getting here is an instantaneous answer. It's the instantaneous solar wind and the instantaneous magnetosphere. So there's some reaction times hidden in there. Now, a curious thing is, and I didn't put it in today's talk because it's complicated to explain, but I can put a flywheel effect term in the driver, and it's a time interval of about 16 hours of what we call the reconnection quick derivation function, and I think it acts as a flywheel, and what it does is, you see on the left-hand side of this plot, it's nonlinear at low driving and low activity. That flywheel term, when I put that in, corrects that, and it linearizes that really low activity thing. So there is, in a sense, we can see a little bit of a flywheel effect, and it's about 3/4 of a day or so is that time scale.
So we're just a little bit over, but I'm going to merge my question with Mervin's question to finish. So I was wondering whether you had how you'd picked the components of the state vector, and Mervin was wondering how important each of those components are, and if you can selectively remove them to see how important they are.
Well, we have done that in our studies, and we have I think 4 papers that go through these studies. Basically, we take a set of Earth variables, and then we add solar wind variables, and if they make a difference, we keep them in the state vector, and if they don't make a difference, we leave them out. And so the 8 variables that you see here are ones that the system likes. And if I take out any of those variables, it knocks down the correlations I get. So these are the real solar wind variables that we can get our hands on that the system really likes. And now the same thing when we go into the magnetosphere. If I add an index that describes the state of the electron radiation belt, it really doesn't want that variable because it doesn't really act the same as the system. Now it will show up in like E2 or E3, it'll show up. It'll want it for a different mode of reaction to the magnetosphere. But for this basic driving mode, it doesn't really want that variable. And it'll give it a very low coefficient. And if you take it out, it doesn't really make a difference.
Okay, thank you.
Sure, guys.
So we've got, I think it's 15 or so minutes left until we have to end this chat. It's a discussion time, right, John? Is it past?
Yeah, so the meeting officially ends at 12:30, but I believe we actually sneakily have until like 25 or 22. So if we're having a very interesting discussion, we might be able to postpone the end. So yeah, if there are any kind of broad themes or overarching questions people have, if they want to put them in the chat or in the Q&A, and we can start a discussion. And if you want to speak, let me know and I can give you the power to do so. I think, Rob, did you want to unmute and pitch one of the things you had mentioned before the meeting, just to get the ball rolling?
Oh, yeah, I actually have like an entire page of ideas. I'm just going to put it in the chat because I think it might be interesting. Yeah, actually, is that too big for the chat? One moment.
Oh.
Why don't you?
Yeah, I actually think I can get it like half in. Okay. Yeah. 1 second. Let me take that out. Okay. So when I was setting this up, I get this is a start. Okay, this is very much a like a thought dump. Like I've seen a lot of discussion in sort of like various sessions centered around things like, you know, there's a spectrum from sort of pure physics modeling to sort of pure data modeling and data science, and then sort of in the middle you've got physics-based models that assimilate stuff. And I just kind of felt there was a gap between that kind of spectrum and something like developing models which just allow you to interrogate a system in elegant ways. And that's kind of why I proposed a meeting a couple of years ago with the same co-conveners that John has seen fit to take forward. It'd be nice if we could keep something like this going. It kind of depends how people feel about it. I mean, I like these kind of sessions.
Yeah, I think trying to work out a way to make this a sustainable thing is a wise thing to do, because I think there is a clear niche into which this sort of work fits. So I don't know whether just proposing more RAS meetings on these sorts of topics is the best way. Does anyone have any thoughts on kind of how to keep the ball rolling, as it were? And feel free to unmute if you're a panelist.
Actually, yeah. Is there somewhere the participants saying that they would like to speak?
Yes, if participants want to speak, just post in chat and I can promote them. Sandra.
Yeah, I mean, just a couple of thoughts. I mean, there's kind of various different things we want to do. One is we want to go, yay, I've got a nice result, which is great, and that's interesting. But then there's I mean, it's like my little talk. There's a whole load of underlying methodology that there's no way I'm going to get in that talk, okay? But you know, afterwards you talk to people and you say, well, actually, you need to do this and you need to do that. So to have meetings kind of just kind of methods, okay? And so the things, it seems to me, but you want to kind of not just here's my great method. What you know, the problems. So what problems do you want to solve? You know, what's the question? And I mean, we could come up with a list, but I mean, just off the top of my head. One is null hypotheses. You know, here is a nice thing. I did this, I did that. Look, this goes up with this goes up with that. Where's the null? How do you set up a null hypothesis? It's actually quite tricky. I mean, what we did with the networks, I mean, we actually did something which is standard is random phase surrogates, that you say, well, I'm claiming a correlation. So I'm claiming a time structure. Therefore, I'll take the data and I will preserve its statistical properties. I'll preserve its power spectrum, but I will shuffle the phase information and shove it through and see, you know, how likely all this stuff is to happen by chance. So, but a different problem, you'd want a different random phase surrogate. So, you know, that's kind of one thing, is how you construct these things. And it's quite tricky because when you're going from, everything from, I'm just looking like this ampere data or the supermag, everything's moving around. And so I think there's all kind of correlation of space and time scales all getting folded in, you know, and so it's really how do you set, so thing number one is random, you know, is the null hypothesis. How do you do that? So I think it's non-trivial. And the other one is how you make all these maps. We've all got these maps, you know, and there's all different ways. There's assimilating, there's the networks, there's, you know, there's infilling using data from the past. You know, I've got a big hole. How do I fill that? Again, there's a whole lot of things to talk about there, it seems to me. So there are specific, I mean, I'm sure there's other things, but just, you know, you could have a whole day on one of these. You could literally have a session, just let's talk about how we make these maps and what the maps mean and what different maps. The other one is parameterization. As I say, you go around, here are lots of maps showing something interesting for one event, and I've got 50, you know, how can I boil down the information that I'm using my eye to see in that map? You know, this is interesting, into kind of a number that varies with time, so I can compare it with 50 others, you know, this kind of thing. And each of these, they're not, it's an easy question to answer. And everybody, it seems we're all attacking this, you know, and there's other ones as well, like what Joe Roski's talking about, this kind of how you put together multiple variables and, you know, all this stuff. You know, you could sort of just have a day talking about one of these things, and maybe a series, you know, of RAS or whatever, where we just do 3 or 4 of these, and each one you kind of do a different topic, you know, and you know, I'd get a lot out of that anyway. So that's why I suggest it, because there are lots of standard things out there that you can do, but you have to think a little bit when you apply them, to be honest, you know, so you can't just, you know, it's not trivial. So that's my thought. My only other thought is, we have all these STFC summer schools. Couldn't we have one like on all these methods? You know, or you know, it's nice to talk about. I know you want the one. This is what the solar system is. There's a nice picture of the magnetosphere. Blah blah blah. You know, but one on methods. You know, for all the new PhD students. That's my other suggestion.
That would actually, because the STFC have deprioritized the advanced summer school, that could be a good way of pitching the advanced summer school at some point in the future. Because I know they're keen to move more towards a topical advanced summer school that kind of either tackles kind of big data topics or interdisciplinary or things like that. So yeah, that's a good thought. Martin and Malcolm have been typing in the chat. So Martin wonders whether or not Earth and space science could be a useful place to review and share techniques. And Malcolm says, sounds like an ISI working group to me. I'm planning to put in an ISI working group to the next call, but you know, there's a high risk that won't happen, and also it's quite limited. So I think that's a good idea, but it would be cool if we could do something more inclusive, I guess. Like an ISI working group is obviously you decide who you want to have and then you set it up, whereas I think having a forum we could do it in the UK would be really nice. Joe.
One easy thing to do would be to have a virtual monthly seminar with maybe a half hour afterwards for just general discussion for the attendees.
That's pretty much what I was going to say.
Run that from home, you know, you don't have to have any official stamp on it, or you can invent it and own it.
Yeah, so Martin has suggested, Martin and Katrina have suggested similar in the chat. So one of the things we will find out when the results of the RAS February round, it's March right now, right? Oh no, it's April. When the February round of the RAS grants comes out with success or failure, one of the things that missed in UKSP put in was having our own Zoom license where we could run kind of more ad hoc events. And so being able to, if that is funded by RAS, then we could potentially do a regular series of kind of hourly or 2 hourly meetings on that. So that is potentially a very good idea. And that's something we could easily do.
I would really like them in the format that EGU runs special sessions. Obviously at normal times, just like hour-long, I forget what they're called, but just to like workshopy teaching ones to learn about methods. I went to one of those and I found it was really, really useful. I think it's the exact format we'd want for methods in this as well.
That's a really good idea.
Yeah.
So coming back to, again, what Sandra was saying, like a lot of this is like, people are facing like vaguely common problems. So I think the uptake of these could be like at least wider than it currently is. But also you need that expert input, because it kind of part of the question of this system scale kind of stuff is, what are you fine with averaging over in order to get your sort of system level understanding of it? And that needs kind of expert input, I think.
And to help with your sustained effort phrase, which is totally right, having a place to keep all these recorded talks and any resources that we come from them would be really useful as well, even if it's just, you know, a really simple website where we just have links. But to make it a community sustained effort, just links to the different methods, because I feel like it's the methods that we all have the same or similar underlying knowledge of the physics. It's the methods that we're all working on in different little bubbles.
Yeah, and that's something like if we wanted to have somewhere to host the resources, we could have like a page on the MIST website for that relatively easily. Or we could like spin up a github.io page and have it be a community repo, as it were. So there's a couple of different options there, I think. Does anyone else have any thoughts on this? Feel free to, if you want to speak, just post in the thing. And Katrina has suggested that a method session could be a springboard for community code sharing. And so that was one thing I was going to ask. Like, so one of the things that occurred to me in Sandra's talk that I didn't ask afterwards was, is that method you're using something that is like a Python library or something similar? Is it easy for people to kind of use themselves, or is it something that people have to re-implement it kind of from scratch if they want to?
Lauren can answer. I think she.
Yeah, I can probably answer.
I'll let Lauren answer. I don't need to.
Yeah, some of it is and some of it isn't. It's MATLAB code. A lot of it is homemade, but the underlying functions are all in MATLAB. So there's loads of wavelet functions. There's wavelet correlation functions that are quite simple, and there's a lot of MATLAB just background how to use wavelets as well. So it was quite easy to figure out. But yeah, the code itself is currently not online anywhere, and probably quite a mess, but could be tidied up. But yeah, I guess sharing like even useful correlation functions and wavelet functions and things that are on MATLAB or Python or anything is also useful.
And the other thing is, that, I mean, not for the stuff with the power grid, but the other stuff, Lauren, I know you use these network packages, so the network scientists have a load of stuff, don't they?
Yeah, my code for the communities paper is all online on GitHub. And yeah, there's loads of network stuff on MATLAB as well. And the cross correlation that Joe was using, they've got good cross correlation, canonical cross correlation analysis stuff on MATLAB as well. And Python, I've used that too.
So Martin asks, does our community have avenues for more traditional recognition for non-science paper outputs? Which is the consistent question that no one has a good answer to, right? Because the answer is no, but it should, which is unhelpful because academic papers are ingrained in the community as a method of recognizing worth at a level which is difficult to unpick as a meeting of 30. Does anyone have any less pessimistic takes on that? Martin, do you want to say anything on the topic? I've pessimistic. Oh, Sandra, yes.
I can make a suggestion. And this comes from the medics, okay? And there was, I don't know if they've implemented it, but it was a while ago. The suggestion was, it's a bit out there, but the idea is you separate the procedure from the analysis. So in other words, if you think about the way you do a paper, you know, like my network stuff, okay, I want to answer the question, you know, what's the substorm current system doing, blah, blah, blah. And then I come up with a procedure, which is this network thing. And then I come up with a random phase, a surrogate to, you know, null hypothesis. And it's all in there, okay? But the idea would be that you write a paper that's saying, this is the question I want to answer. And this is the analysis that I would propose to do. You know, that this, and I would need to see this. This would be like, yes, no. If I see this, then my hypothesis is proved. And if I get that, then it's not proved. This would be what would be required without actually doing the analysis. And that is a peer-reviewed thing. Okay, and then somebody else can come along and do the analysis, and they could get a paper as well, you know, or more than one people could do the analysis. So it kind of makes a space, because what doesn't get published is when it doesn't work. You know, you try and test this idea, or, you know, and then you get your data, and it does actually, it's just a mess. You know, it doesn't. Whereas this kind of does that, and it kind of breaks these things apart. And it really kind of, the reason the medics are interested is they're worried about confirmation bias. That you know, I've got my idea that this drives that, and I go and find something in the data that agrees with me, and I publish a nice data saying, see, you know, on a Tuesday, this indeed did that, you know. And I'm not saying everything's like that, but there's a kind of tendency to do this, or at least I've got evidence that on a Tuesday it did it and I haven't finished it, blah, blah, blah. So separating these things out. So, you know, but it's a bit of a paradigm shift, because you'd have to have a journal that actually, you know, would publish that basically you would accept that, you know, this is a creative new result, is how you would go about this. And what procedure would definitively, you know, tell you whether, you know, this hypothesis is correct or not. How much evidence would you need? What would be sufficient evidence? What would not? How would you, you know, all that guff. So, and that includes all these methods. So, you know, saying that I think you should use this method and this method, you know, or that would be in there. So you'd kind of get the credit for that, even if you haven't actually gone. So you might find, I want to test that substorms do this on a Tuesday. You might find actually they don't do it on a Tuesday, but you'd still get the credit for proposing how you do it. Even when you then, somebody else then gets the credit for a null result. They can publish a paper saying, I tried what you said and it didn't work. And that to me is really powerful as well, you know, that you should be able to publish null results. And what is null about them, you know? So that's my suggestion. As I say, this is from the medics because of confirmation bias, but it's a different way. It's a bit of a paradigm shift, so I don't know if it's achievable. Okay.
I think it is a paradigm shift. So JGR has JGR techniques. I can't remember if it's called techniques or methods now. But there is a.
I thought it disappeared again. I don't know.
Oh, did it? Oh, that's a shame.
I don't know if it disappeared. And I've published in it. Our first network paper, that's how we published it.
Yeah, I published in it too. I published my cluster load kind of framework in there before I did a paper that used it. So like there's definitely work being done to advance that. And as Steve points out, Steve and Sarah in the chat point out other places you can do this. So I think it is possible to adopt that approach, and I think it would be potentially very useful to publish the methods as well as publishing the results. I think Mervyn has their hand up, so I'm going to ask him to unmute.
Yeah, I was just going to comment on what Sandra was saying, that what you described sounds quite similar, a sort of modern day version, if you like, of theory papers, basically, classical theory papers. I mean, you make a prediction based on, you know, on some some physical thing, and somebody else goes along and proves it for you. I mean, you're setting up a construct that is to be tested.
It's more than that. That's part of it, but then there's specifically, you know, how you do it, how you test it with the data, how you construct a null hypothesis for the data.
Sure.
You know,
No, I understand.
The theory is just the start, I think.
No, I understand what you're saying. I'm just saying that you can draw parallels to what is already established, and maybe you should exploit that parallel, is what I'm really arguing.
Makes sense. Yeah, and I think that's something that we can ask in further monthly seminars and such like dedicated to this theme. So I will, if everyone who has attended, who is listening now, I'm going to put my email address in the chat. If everyone who's attended could pop me an email just so I know you were here. If you presented a talk, you don't need to because I've already got your details, but if you didn't, then please do let me know. And then when I hear from the RAS's grants scheme as to whether or not we have funding, then I can email you all and let you know that we will start some sort of monthly persistent thing. And I'll also, if that happens, make it known through the MIST mailing list and the SPA and CEDA mailing lists and all of those good places. I think we're probably out of time. So one thing I would like to do is if you spoke at the meeting and you haven't sent me your slides, please do so, because we'll be writing up this session for astronomy and geophysics, and having references to refer back to is really useful. And if you could also send me a couple of sentences if you are particularly keen to make sure that we describe your talk just right in the write-up, then feel free to do that too. And yeah, thank you all very much. Thank you to my lovely co-organizers for being amazing. And thank you very much to everyone who spoke and discussed things here at the end, because I think that was also super valuable. I have had a wonderful day, and I hope everyone else found it interesting too. Thank you all very much for coming, and see you at the first monthly one. Fingers crossed.